Chemistry runs on three different definitions of what counts as an acid, all of them official, all of them still taught side by side, and they do not fully agree with each other. A chemist working under one definition will call a substance an acid. A chemist working under a different one, just as trained, just as correct by the rules of their own definition, will say it is not. Boron trifluoride is a clean example. It grabs an electron pair the moment ammonia gets near it, which makes it an acid under the broadest of the three definitions, the one built by Gilbert Lewis. But it never gives up a proton. So, under the definition built by Johannes Bronsted and Thomas Lowry, it doesn't behave like an acid at all, and dropped into water, it doesn't dissolve cleanly enough to even get tested fairly. Under the oldest of the three, the Arrhenius definition, three real published competing rules for one of the very first words a chemistry student ever learns, and nobody in the field has ever forced them to agree. That isn't really a story about acids. It's a story about how chemistry teaches itself. This is a tour through the parts of the subject that are confusing on purpose, or at least confusing for reasons nobody bothers to explain at the time they happen. Some of it is small stuff, units and naming habits that trip people up out of pure convention. Some of it is bigger, whole models handed over as if they were the entire truth, then swapped out later for a messier, more accurate one, with no warning that a swap even happened. And sitting right in the middle of the subject are two ideas, entropy and equilibrium, that trip up more students than anything else in chemistry, for reasons that are actually documented and studied, not just staff room folklore. Start with something that looks simple on the surface. The pH scale was invented by a Danish chemist named Soren Peter Lauritz Sorensen in 1909, working at the Carlsberg Laboratory, the research arm of the beer company. He needed a workable way to describe how acidic a solution was without writing out long strings of decimals every time. So he built a scale based on the negative logarithm of the hydrogen ion concentration. Chop 9 zeros off a number and call it a 9. That part is straightforward enough. What nobody agrees on, and what Sorensen himself never explained in his own writing, is what the letter P in pH actually stands for. It might be the French word for power, puissance. It might be the German word potens, since German was the dominant language of scientific publishing at the time. It might be the Danish word potens, since Sorensen was Danish. Some later writers have guessed at a Latin phrase instead. Sorensen used a second letter, Q, in a similar way elsewhere in the same paper, which makes some historians think he was just labeling a test solution P and a reference solution Q, almost arbitrarily. Over a century later, every pH meter and every worksheet in the world still carries that letter, and nobody actually knows for certain what it was supposed to mean. Sorensen doesn't even get an entirely uncontested claim to inventing the idea in the first place. An American bacteriologist named Alice Catherine Evans, working in the 1910s, later credited a different scientist, William Mansfield Clark, and his own collaborators, herself included, with independently developing practical methods for measuring hydrogen ion concentration around the same general period, describing in her own memoir how Clark had noticed that bacterial growth depended specifically on the intensity of a solution's acidity instead of the raw quantity of acid present, and had built accurate new measuring methods to track it, methods that ended up spreading widely through laboratories and industry, regardless of how much they overlapped with Sorensen's own work, happening at almost the same time. The first fully electronic way to measure pH directly didn't arrive until 1934, invented by a chemistry professor named Arnold Orville Beckman at the California Institute of Technology. And it wasn't built for any grand scientific purpose at all. A local citrus grower, the Sunkist Company, needed a faster, more reliable way to test the acidity of lemons fresh off the tree, and Beckman's meter, developed to solve that specific, unglamorous commercial problem, became the direct ancestor of every electronic pH meter used in a lab or a swimming pool today. The scale itself causes its own trouble. Pure water sits at a pH of 7, which counts as neutral because the concentration of hydrogen ions and the concentration of hydroxide ions are equal there. Below 7 counts as acidic, above 7 counts as basic. Students get taught that the whole range runs from 0 to 14, and for a beginner chemistry class that's close enough to be useful, it isn't a hard boundary at all. The scale is logarithmic. This means a pH of 3 isn't a little more acidic than a pH of 4. It's 10 times more concentrated in hydrogen ions, and a pH of 2 is 100 times more concentrated than a pH of 4. Push a strong acid to a high enough concentration, and the pH can go negative. Runoff water draining out of active mines has been measured at a pH of negative 3.6. Push a strong base far enough the other direction, and it can go past 14.2. Even the neutral point everyone memorizes, that clean pH of 7, shifts with temperature because the self-ionization of water itself depends on temperature. 7 is really just the neutral point. At 25 degrees Celsius, ordinary room temperature, dressed up as though it were a universal constant. Warm the same pure water up, and neutral drifts below 7. Cool it down, and neutral climbs above 7. The water never actually changes. Push the concentration of a strong acid low enough instead, thin enough that there's barely more of it than the water it's dissolved in, and pH stops behaving in the clean, one-step way the classroom formula promises, since water's own tiny natural tendency to split into hydrogen and hydroxide ions on its own stops being small enough to ignore, and the real pH ends up sitting measurably away from what the simple formula alone would predict. Even calculating a pH from scratch hides a piece of real mathematical work behind a number that looks like it should come from a single plug-and-chug formula. For a strong acid, one that falls apart completely in water, the calculation really is simple. Since the concentration of hydrogen ions comes out equal to the acid's own starting concentration, and the pH follows in one step. A weak acid, one that only partly falls apart, forces an actual quadratic equation into the calculation instead, because some of the acid stays whole and some splits apart. And working out how much of each requires solving for an unknown concentration. Instead of reading it straight off the bottle, take a solution of benzoic acid, a real, everyday preservative with a known acid strength constant. Solving the resulting quadratic by hand lands on a pH of about 3.11 for a solution that started at a concentration of 1/100th of a mole per liter, a small enough example to work through on paper and a genuine warning sign for anything more complicated. A weak base needs a cubic equation instead of a quadratic, one full algebraic degree harder, and any solution dilute enough, or close enough to neutral, forces water's own self-ionization into the calculation as well, since water acts as its own weak acid and weak base at the same time and can no longer be ignored the way an introductory formula usually gets away with ignoring it. There's a second wrinkle that barely ever makes it into an introductory class. Scientists who study the ocean use pH constantly, since ocean chemistry runs on dissolved carbon dioxide turning into carbonic acid. But seawater is different enough from the simple solutions in a chemistry classroom that oceanographers actually work with 3 separate pH scales at once, and the 3 don't always agree. One version, called the free scale, ignores the effect of dissolved sulfate and fluoride ions entirely. A second, the total scale, accounts for sulfate. A third, the seawater scale, accounts for both sulfate and fluoride. In practice, the 3 scales can differ by as much as 1/10 of a pH unit. This sounds tiny at first, easy to forget the scale is logarithmic and that oceanographers routinely need better precision than that. Between 1950 and 2020, the average pH of the surface ocean dropped from around 8.15 to around 8.05 as the ocean kept absorbing carbon dioxide out of the air and turning it into acid. That's a real, measured, worrying shift, and reporting it accurately depends on picking the right one of 3 competing versions of a number every science student is taught is just one simple thing. Human blood runs at a pH of about 7.365, just barely on the basic side of neutral, and the body works hard to keep it inside an extremely narrow band. Push it much lower, and doctors call it acidosis. Push it higher, and it's alkalosis. A single number, logarithmic, temperature dependent, and defined by a letter nobody can fully explain, is doing an enormous amount of work every single day inside a living body. pH indicators work off a similar chemistry the moment it becomes something visible. A universal indicator is really a mixture of several separate dyes blended together, each one changing color across its own narrow slice of the pH range. So the combined mixture sweeps smoothly through a whole rainbow of color as pH climbs from around 2 up to around 10. Plenty of that same chemistry already exists in nature with no laboratory involved at all. Red cabbage, hibiscus flowers, and the pigment inside red wine grapes all carry natural pH sensitive dyes of their own. This is why red cabbage juice famously swings from red through purple to green and yellow as the liquid around it moves from acidic to basic. Measuring pH with real electronic equipment gets harder, not easier, right at the extreme ends of the scale. This is a strange thing for a scale supposedly running cleanly from 0 to 14, below roughly a pH of 2.5, and above roughly a pH of 10.5. Standard glass electrodes start giving unreliable readings, partly because the electrode's own underlying chemistry stops behaving as cleanly at extreme ion concentrations, and partly because of something called alkaline error, where a glass electrode sitting in a highly basic solution starts mistakenly responding to sodium and potassium ions floating around in the solution as though they were hydrogen ions, throwing the reading off. In 2010, a group of researchers proposed an entirely new approach called the Unified Absolute pH Scale, built around the chemical potential of the hydrogen ion instead of a simple concentration measurement, specifically because it could be applied consistently across liquids, gases, and even solids, something none of the older pH scales, including the three separate ones oceanographers already juggle, could manage all simultaneously. Even something as ordinary as cooking runs on pH in the background. Acidic foods, tomatoes, citrus fruit, vinegar, generally sit below a pH of about 4.6, sharp and tangy, specifically because of that low pH. And food scientists treat that number as a real, practical safety threshold, since it's roughly the point below which most harmful microorganisms struggle to grow at all. The Maillard reaction, the browning that gives seared meat and toasted bread their flavor and color, is pH sensitive too, running faster or slower depending on how acidic or basic the food happens to be while it cooks. None of that requires any chemistry background to notice. It just requires knowing that the same logarithmic, oddly defined scale running through blood and seawater and mine runoff is running the kitchen too. The pH scale doesn't even travel outside water cleanly. Measuring acidity in a solvent that isn't water at all requires its own separate scale. Since the standard reference point pH is built around the concentration of hydrogen ions, specifically in water, simply doesn't carry over to a different solvent in any directly comparable way. This means a pH measured in one non-aqueous solvent cannot be compared straight across to a pH measured in a different one. For extreme acids, stronger than anything water itself could ever measure or even survive contact with, chemists reach for an entirely separate scale altogether, called the Hammett acidity function, purpose-built for so-called superacids, compounds strong enough to protonate substances that ordinary acids can't touch at all. pH, in other words, isn't even the last word on acidity within its own family of measurements. It's the version that happens to work for water, sitting alongside a whole cluster of other acidity scales built for whatever water can't handle. The ground underfoot runs on the exact same number. Government agencies that classify soil quality sort dirt into named categories, running from strongly acidic through neutral to strongly alkaline, purely by pH, since what grows in a given patch of ground depends heavily on where its pH happens to sit. And a map of topsoil pH across Europe shows a striking pattern: more alkaline soil clustered around the Mediterranean, Hungary, and parts of eastern Romania and northern France, and noticeably more acidic soil across Scandinavia, Portugal, Poland, and northern Germany, a pattern driven by the underlying rock, the local climate, and centuries of whatever's been growing there. Plants carry pH sensitivity inside their own tissue too, not just around their roots. The same natural dyes that make hibiscus flowers and red cabbage change color under different pH conditions exist because plants use pH-sensitive pigments for their own internal chemistry. And citrus fruit gets its sharp, sour taste specifically from citric acid, lowering the juice's pH just like vinegar or lemon does. Inside the human body, pH sensitivity runs right down to individual proteins. Every enzyme in the body has its own narrow, specific pH range where it actually works properly. And pushed outside that range, an enzyme can lose its functional shape entirely, a process called denaturation, the same basic mechanism that turns a raw egg white opaque and solid the moment it hits a hot pan. Tooth decay runs on the identical chemistry at a much smaller scale. Since bacterial plaque sitting on tooth enamel can create a small, locally acidic pocket that slowly dissolves the mineral structure of the tooth underneath it, one more place where a shift of a fraction of a pH unit, invisible to the naked eye, decides whether something as ordinary as a tooth holds together or doesn't. Move one step further into a first-year chemistry course, and there's oxidation state, sometimes called oxidation number, the little superscript figures written after element names in parentheses, like iron, with a Roman numeral 3 trailing behind it. Students get taught to treat these numbers as though they describe something real about the atom, some literal count of electric charge sitting on it. They don't, not even close. The International Union of Pure and Applied Chemistry, the body that sets the official rules for how chemistry gets named and defined, ran a formal project from 2008 through 2016 just to pin down a single clean definition of oxidation state. And the definition that project settled on says plainly that oxidation state is the charge an atom would have if every one of its bonds were pretend converted into a fully ionic bond, with the shared electrons handed over entirely to whichever atom is more electronegative. That phrase, ionic approximation, is doing a lot of quiet lifting. Real covalent bonds don't actually hand electrons over completely to one side. The electrons in an ordinary carbon-hydrogen bond, for instance, are shared close to evenly. Oxidation state throws that nuance away on purpose and assigns the electrons all or nothing anyway, purely as a bookkeeping convenience. The bookkeeping is useful bookkeeping, which is why it survives. It helps balance equations. It explains why compounds get named the way they do, and it tracks electron transfer in oxidation and reduction reactions well enough to be worth teaching. A classic laboratory test for detecting a particular kind of poison, arsenic, works purely off that bookkeeping. Mixing a suspect solution with tin chloride produces a visible dark stain of solid arsenic, precipitating out the instant arsenic is present. And chemists explain why by simply tracking oxidation numbers through the reaction. 3 tin atoms climbing from +2 up to +4, releasing exactly enough electrons to drag 2 arsenic atoms down from +3 to 0, an old, still useful forensic test built entirely on numbers that were never claiming to be real physical charges in the first place. Carbon alone can carry 9 separate whole number oxidation states, running from -4 up to +4, depending purely on what it happens to be bonded to, working perfectly well because nobody involved ever needed those numbers to be anything more than convenient. Treat it as a real physical property, and it starts breaking almost immediately. Different scales for measuring how strongly an atom pulls on shared electrons, called electronegativity scales, can hand back different oxidation numbers for the exact same molecule. Using the Pauling or Mulliken electronegativity scales, platinum in one particular hydride compound comes out with an oxidation state of -6, a number nobody would guess just by looking at the real electron distribution in that molecule. Carbon monoxide and nitric oxide both have their positive ends pointing toward the oxygen atom based on their actual measured dipole moments, which runs backward from what the standard oxidation number assignment would predict. So chemists set the dipole measurement aside and use a different rule instead, just to keep the numbers behaving the way the convention needs them to. The record numbers get stranger the further the search goes. Iridium has been measured at an oxidation state of +9 inside a molecule called tetroxoiridium, the highest confirmed oxidation state ever recorded for any element. Researchers have predicted platinum could theoretically reach +10 under the right conditions. On the other end, boron and gallium have both been recorded at -5 in certain compounds. Some oxidation states aren't even whole numbers. Average out the iron atoms in magnetite, the naturally magnetic iron oxide, and the result is an oxidation state of 8/3, a fraction. because 2 out of every 3 iron atoms in the crystal are really sitting at +3, and 1 out of 3 is really at +2, and the fraction is just the average of the two hiding inside one number. Ordinary propane gas gets the same fractional treatment for a slightly different reason. Averaged across all 3 of its carbon atoms, propane's carbon sits at an oxidation state of -8/3. But no single carbon atom in the actual molecule carries that number, since the two end carbons each sit at -3, and the middle carbon sits at -2, and again the fraction is nothing but an average smoothing over 3 different real values. Potassium superoxide goes a step further and produces a fraction that's actually real instead of just an averaging trick, because its 2 oxygen atoms are chemically equivalent to each other by the symmetry of the molecule, sharing one single negative charge evenly between them. This forces each individual oxygen atom to carry an oxidation state of -1/2, a true fraction assigned to a single, specific atom instead of a population average standing in for several different real atoms at once. Some molecules refuse to settle on even a single whole number answer, despite having every atom pinned down exactly. Phosphorus acid, a real ordinary compound, has its central phosphorus atom sitting at an oxidation state that gets assigned as +3 by the convention most textbooks default to, purely because that's the simplest, most pedagogically convenient choice, even though a careful reading of the actual measured electronegativities involved points by a narrow margin toward +5 instead. Chemists studying the compound closely have concluded that both numbers make genuine chemical sense, depending on which specific property or reaction is being emphasized at the time. This property of the molecule someone's actually trying to explain, and that picking one isn't a matter of finding the objectively correct answer so much as picking the more useful lens for the specific question being asked. Averaging the two disputed numbers together, landing on +4, is explicitly the one option that makes no chemical sense at all, since +4 doesn't correspond to any real structural picture of the molecule whatsoever. A related molecule, a square-shaped ring built from 2 sulfur and 2 nitrogen atoms, forces the same kind of averaging on chemists in a slightly different way. 4 separate, equally valid resonance drawings of the molecule each assign its 2 sulfur atoms oxidation states of +2 and +4. And because the molecule's own real geometry treats both sulfur atoms as fully equivalent to each other, the only sensible number to report for either one is the average of +2 and +4, +3. A fractional feeling answer arrived at honestly this time by averaging 4 equal valid pictures instead of picking one preferred convention over another. Oxidation state was never trying to describe reality that precisely to begin with. It was built as a convention for keeping equations balanced, and it does that job well. It was just never meant to be read the way most students are taught to read it, as a fact about the atom itself. The naming convention around oxidation states has its own tangled history too. Older chemistry used a pair of Latin endings, IC for the higher oxidation state and aus for the lower. So iron chloride at the higher state was ferric chloride, and at the lower state was ferrous chloride. That system fell apart the moment anyone tried to apply it consistently, since the exact same endings meant different actual numbers depending on the metal involved. Ferric and ferrous standing for +3 and +2, while cupric and cuprous, built off copper, stood for +2 and +1 instead, and stannic and stannous, built off tin, stood for +4 and +2. A chemist in 1919 named Alfred Stock proposed replacing the whole confusing pair of endings with a plain Roman numeral written right after the element's name, iron 2 chloride instead of ferrous chloride. And the International Union of Pure and Applied Chemistry formally adopted his system in 1940. The older Latin endings never fully disappeared, and both systems still show up side by side in real chemistry writing today. Even the term oxidation state itself only entered common use fairly late, popularized specifically by a chemist named Wendell Mitchell Latimer in a 1938 book about electrochemical potentials, replacing an older term, valence, that had been doing roughly the same job under a different name for decades before that. Before any of these later refinements, a chemist named Friedrich Wöhler had already been calling early versions of the idea oxidation grades as far back as 1835. And Dmitry Mendeleev himself leaned on the regular, repeating pattern oxidation states show across the periodic table as one of the actual pieces of evidence guiding him toward building the table in the first place. Decades later, in 1919, the chemist Irving Langmuir used a chart of oxidation states across the elements as direct supporting evidence for a completely different, brand new idea he was developing at the same time: the octet rule, the now familiar notion that atoms tend to gain, lose, or share electrons until they reach 8 in their outer shell, showing how one piece of chemical bookkeeping ended up propping up an entirely separate foundational theory built decades afterward. Plenty of individual compounds still resist a clean, agreed oxidation number, even after all of that formal standardizing. Assigning an oxidation state sometimes requires an actual physical measurement instead of any amount of careful counting on paper. A nickel compound built around a particular sulfur-containing ligand hides its true redox behavior so effectively that chemists can't confidently assign nickel's oxidation state from the structure alone at all, and have to fall back on spectroscopic or magnetic measurements instead. A related manganese compound sits balanced closely enough between two different oxidation state assignments that it actually flips between them depending on temperature, a phenomenon called thermally induced tautomerism, meaning the same molecule can hold two different, both technically valid oxidation states depending on how warm the sample happens to be at the moment somebody checks. Thiosulfate, a common ion built from 2 sulfur atoms and 3 oxygen atoms, has 2 competing, chemically reasonable structures on paper, and settling which one actually describes the real molecule takes a direct measurement of the distance between its 2 sulfur atoms, since the bond length itself is what finally tells the 2 possible drawings apart. Even ordinary metal alloys throw the whole convention into a corner. Materials like a lithium-lead alloy or an ordered mixture of copper and gold are held together mostly by loose, shared, metallic electrons that don't belong to any one atom in particular. And trying to force a specific oxidation number onto any single atom inside a structure like that stops making real sense. Chemists handle it by simply setting the oxidation state to 0 for every atom in an alloy like that whenever the bookkeeping actually needs one, a quiet admission that the entire convention, everywhere it's applied, was built to serve chemistry's need for tidy bookkeeping first and physical accuracy a distant second. Balancing a chemical equation looks like the one clean piece of arithmetic in the whole subject, whole number ratios of atoms, nothing fuzzy about it, and even that turns out to carry a small asterisk once real measurement gets involved. Ordinary ammonia, built from 1 nitrogen atom and 3 hydrogen atoms, should by the clean whole number ratio weigh out to exactly 14 parts nitrogen for every 3 parts hydrogen. Weighed on a real laboratory balance, it doesn't come out quite that clean because natural nitrogen isn't one pure isotope. It's a mix, mostly the common, lighter form with a small admixture of a heavier isotope, nitrogen-15, and natural hydrogen carries its own small admixture of a heavier isotope too, deuterium. The whole number ratio driving the chemistry is exactly right. The actual measured mass ratio on a scale is very slightly off from that clean whole number, purely because of isotopes nobody accounts for at the level the whole number rule is taught. Even the cleanest, most reassuringly exact piece of arithmetic in the entire subject turns out to be a slightly idealized rounding of what a real balance would actually show. Even naming a molecule turns out to be its own entire discipline. The official rules live in a real published reference chemists actually call the Blue Book, put out by the same international body that argues over oxidation states. And the naming process is not casual. A chemist doesn't just describe what's in a molecule. There's a fixed order of operations. Find the most important functional group present. Find the longest chain or ring that contains the largest number of that group. Number the chain in whichever direction gives the lowest possible numbers to the important pieces first, checking one tiebreaker rule after another until a winner falls out. Then list every other piece attached to that chain in strict alphabetical order, and the alphabetizing carries its own trap, since prefixes like D and tri that just count how many of something there are get ignored for alphabetizing purposes. That's why a molecule carrying 1 ethyl group and 2 hydroxy groups gets written with ethyl listed first, even though ethyl starts with E and dihydroxy starts with D, because officially it isn't being alphabetized against dihydroxy at all. It's being alphabetized against hydroxy, with the D silently stripped out first. A student can get every atom of a structure exactly right and still get the name wrong, purely on an alphabetizing rule nobody ever warned them about. Naming ions carries its own small oddity worth pointing out. Sticking a hydrogen ion onto an ordinary nitrogen, oxygen, or fluorine hydride produces a new positively charged ion with the ending onium tacked onto the element's name. So hydrogen plus ammonia gives ammonium, and hydrogen plus water gives oxonium, more commonly just called hydronium. Nitrogen breaks its own naming pattern here on purpose. The strict rule would technically produce nitronium for the ammonium ion, but chemists deliberately kept ammonium instead, specifically because the name nitronium was already taken, reserved for a completely different, unrelated nitrogen-oxygen ion important in its own separate branch of chemistry. One more small case of a naming system bending its own official rule to dodge a collision it had accidentally set up for itself. Plenty of everyday chemical names skip all of that entirely. Water never gets called dihydrogen monoxide outside of a joke. Acetone keeps its old common name instead of turning into some strict, systematic mouthful. And the Blue Book itself explicitly keeps a short list of these older, trivial names permanently acceptable, right alongside the systematic ones. Acetic acid and ethanoic acid are both correct names for the same molecule at the same time, one a holdover from before systematic naming existed, one built fresh from the rules, and chemists switch between them without much thought. Ethanol has mostly pushed out its older name, ethyl alcohol, in modern use, even though both are technically fine. There's no consistent logic to which trivial names survive and which get replaced. Valency itself, the plain count of bonds an element typically forms, follows the periodic table cleanly for light elements. Then the pattern just stops. Transition metals routinely show several different valencies at once, since two closely spaced electron shells compete for the same job. It comes down to habit and to how clumsy the systematic version would have sounded if it had won out instead. The name is only the beginning of the problem, because a single molecule, as plain as ethanol, can also be written down on paper in half a dozen different ways, depending on what a chemist happens to need shown at that moment. A full structural formula spells out every atom and every bond explicitly. A condensed formula compresses the whole thing down to a short string, like the letters and numbers stacked into one line. A three-dimensional formula tries to show the actual spatial arrangement of the atoms, separating the molecule's reactive functional group from the rest of it produces yet another version entirely, and reducing the whole thing down to a bare count of atoms produces a fifth, stripped of any structural information at all. Every one of those is correctly, unambiguously ethanol, and the chemist reaches for whichever version carries exactly the information relevant to the conversation and drops the rest. This means the same substance rarely gets written identically twice inside a single chemistry textbook, let alone across different ones. Follow the full rulebook on a complicated molecule, and the resulting name stops looking like language at all. A 23 carbon chain carrying two ketone groups, two double bonds, one triple bond, a bromine, a chlorine, two ethyl groups, a hydroxy group, and a methoxy group, all attached at their own specific numbered positions, comes out as one single unbroken word running the entire width of a page. Every locant number, every hyphen, every prefix stacked in exactly the order the rulebook demands, with a final tag on the front specifying the exact three-dimensional geometry around each double bond. Nobody speaks that name out loud in a lab. Chemists draw the structure instead and reach for the long systematic name only when a database, a patent filing, or a regulatory body specifically requires an unambiguous, machine parsable string with no picture attached. The naming system was never built to be spoken. It was built to be unambiguous, and those two goals pull in different directions, often enough that real chemists mostly avoid saying the full names out loud at all. Sketching the structure on a napkin long before anyone reaches for the actual rule book. All of that is surface level irritation, units, and naming conventions that trip people up mostly out of habit. The deeper confusion starts somewhere else entirely. Chemistry has a habit of teaching a simplified picture of how atoms bond together, letting a student build real intuition on top of that picture, and only later swapping it out for a messier, more accurate picture, without ever quite announcing that the swap happened. It happens first, and most visibly, with the shape of the atom itself, and even earlier than that, with the plain question of what actually counts as a bond in the first place. Every introductory class draws a hard line between ionic bonds, where electrons transfer completely from one atom to another, and covalent bonds, where electrons get shared between them. And the usual rule of thumb for telling the two apart is a difference in electronegativity of 1.7, above that line counted as ionic, below it counted as covalent. That number is a rule of thumb and nothing more, chosen for convenience instead of derived from any sharp natural boundary in nature. Since real bonding runs on a smooth, continuous spectrum from purely ionic to purely covalent, with no genuine cutoff point anywhere along it, sodium cyanide shows the blur in a single compound. Between the sodium atom and the cyanide group, the bond is ionic, with sodium and cyanide behaving as fully separate, independently moving charged particles the moment the salt dissolves in water. An ionic bond like that one doesn't even have a single specific partner the way a covalent bond does. Since ionic charges typically sit somewhere between -3 and +3, every ion in a real salt crystal sits surrounded evenly by opposite charged neighbors on every side, instead of paired off with one specific counterpart, which is exactly why an ionic solid forms a repeating crystal lattice instead of a collection of separate individually recognizable molecules. Inside the cyanide group itself, the bond between its own carbon and nitrogen atoms is fully covalent, each carbon locked tightly to one specific nitrogen instead of floating freely the way the sodium ion does. One compound, two completely different bond types sitting right next to each other. And the plain word bond is doing double duty to describe both without flagging that they're fundamentally different kinds of attraction. Metallic bonding adds a third category entirely, where every atom in a whole block of metal donates its own outer electrons into one shared, delocalized pool that belongs to no single atom at all. The same delocalization idea driving benzene's ring and oxygen's magnetism showing up yet again, this time explaining why metals conduct electricity, bend without shattering, and reflect light back with that familiar metallic shine. The whole idea of a chemical bond took most of a century just to arrive at the electron in the first place. Working chemists in the 17 and 1800s built the concept of a bond entirely without knowing electrons existed. A Swedish chemist named Jöns Jacob Berzelius argued in 1812 that bonding worked through some kind of electrical attraction between atoms carrying opposite charges, decades before anyone had actually detected an electron to explain what that charge even was. By the middle of the 19th century, a handful of chemists, including Edward Franklin, Friedrich August Kekulé, and Alexander Butlerov, had worked out a formal theory of valency, the idea that every element combines with a fixed characteristic number of other atoms purely from patterns in how compounds actually formed, with no underlying physical explanation yet for why those numbers were what they were. It took until 1911 for Ernest Rutherford to establish that atoms even had a small, dense nucleus surrounded by orbiting electrons at all, a discovery that arrived after chemists had already been drawing bonds between atoms in their notebooks for the better part of a century. A Japanese physicist named Hantaro Nagaoka had proposed his own planetary model of the atom even earlier. In 1904, electrons circling a heavy center the way rings circle Saturn. Years before Rutherford's own nucleus was confirmed, chemistry had a fully working, useful theory of the chemical bond long before it had any real idea what a bond was actually made of. This makes the whole subject's habit of teaching a workable, simplified picture before the real underlying mechanism arrives not some modern teaching shortcut at all, but the same basic pattern the field itself was built on from its very beginning. Take methane, the simplest molecule built around carbon. 4 hydrogen atoms locked onto one carbon atom in a perfectly symmetrical shape, every bond identical, every angle the same 102 9.5 degrees. A carbon atom's raw electron arrangement doesn't predict that shape at all. Carbon's electrons sit in one filled inner shell, and then in the outer shell, 2 electrons paired up in a spherical orbital, and 2 more spread across 2 separate lobed orbitals pointing at right angles to each other. Follow that arrangement literally, and carbon should only be able to form two bonds at 90 degrees to each other, using those two lobed orbitals directly. Real methane doesn't look anything like that. Linus Pauling solved the mismatch in 1931 by inventing a new idea called orbital hybridization. His proposal was that the spherical orbital and the three lobed orbitals don't stay separate at all. They mix mathematically into four brand new orbitals, each one part sphere and part lobe, all four pointing outward at exactly the angles methane actually shows. Pauling called the new blended orbitals SB, three hybrids, one part S character, three parts B character. And the idea worked so well at predicting real molecular shapes that it became one of the standard tools taught in every organic chemistry class since. Ethylene, with its carbon-carbon double bond, gets explained with a different blend, sp2, mixing the sphere with only two of the three lobes and leaving one lobe alone to form the second bond. Acetylene, with its triple bond, gets sp hybrids instead, mixing the sphere with just one lobe. Here's what almost never gets said out loud in the classroom. Hybridization is described, even by the chemists who use it constantly, as a heuristic, a simplified picture built to give a clean, teachable orbital diagram that lines up with what a Lewis dot structure already predicts. It isn't the literal quantum mechanical reality of the atom. When chemists run the real calculations, using the actual mathematics of quantum mechanics on a computer instead of Pauling's clean sketch, the hybrid orbitals that fall out aren't clean sp3 blends at all. They come out at odd non-integer ratios, things like sp 2.5, or for methane itself in the most careful calculations, something closer to sp 1.76 instead of the tidy sp3 every student memorizes. Water is a clean, well-known example. The two bonding orbitals on its oxygen atom work out in real calculations to roughly sp4. This is what actually produces water's true bond angle of 104.5 degrees instead of the perfectly symmetrical 109.5 degrees a plain sp3 prediction would give. There's an even older embarrassment buried in hybridization's history. For decades, chemistry textbooks explained molecules with 5 or 6 bonds around a central atom, like phosphorus pentachloride, by claiming the central atom borrows empty d orbitals to expand past its normal limit, an idea usually called expanded octet theory. In 1990, a chemist named Erik Alfred Magnusson published a paper that settled the question by showing, with real computational chemistry, that d orbitals play essentially no role in bonding these molecules at all. Part of the confusion had come from a separate, unrelated fact that d functions are mathematically necessary inside the computer models used to calculate these molecules accurately. This got mistaken for proof that actual d orbitals were physically involved in the bonding. An idea that had sat unchallenged in textbooks for most of the 20th century turned out to be built on a fairly basic misreading of what the computer math was actually doing. Hybridization runs into a second, subtler embarrassment whenever it gets tested against real spectroscopy. Fire ultraviolet light at a molecule of methane and knock a single electron loose entirely, and the remaining ionized molecule turns out to need two distinct amounts of energy to produce, not one, showing up as two separate signals in the resulting spectrum. A naive reading of simple hybridization, treating each of the four sp3 orbitals as identical and interchangeable, predicts only one ionization energy, since knocking an electron out of any one of four supposedly identical orbitals should cost the exact same amount of energy every time. The real two-signal result only falls out once the four hybrid orbitals get treated properly as a blended symmetric group instead of as four separate independent boxes, producing two different energy levels for the resulting ionized states. For a while, this looked like a fatal problem for hybridization itself. It wasn't quite fatal, because the fix turned out to be a mathematical patch, invoking a kind of resonance between different orbital descriptions, instead of any change to the underlying physical picture. But it's a clear example of the simplified model needing outside help just to match an experiment a first-year student could actually run. Real hybrid orbitals also almost never come out as the clean, round S and P fractions, a formula like sp3 or sp2 implies. A rule named after the chemist Henry Bent captures the actual pattern better, describing how the amount of pure S character in a bonding orbital concentrates itself toward whichever attached atom is less electronegative. This is why water's two oxygen-hydrogen bonding orbitals work out in careful modern calculations to something closer to sp4 rather than a clean sp3, matching water's real bond angle far more precisely than the tidy classroom fraction ever could. Chemists who study this closely have given the departures their own specific name, hybridization defects, coined specifically because real S and P orbitals on the same atom don't always extend out to the same distance from the nucleus, and the mismatch grows worse the further down the periodic table an element sits, which is part of why hybridization explains carbon, nitrogen, and oxygen chemistry reasonably well and gets noticeably shakier once applied to heavier elements like silicon or phosphorus. Transition metals need an entirely separate flavor of the idea altogether, mixing in d orbitals on top of the ordinary s and p ones, or in some low electron count cases, skipping the p orbitals altogether and blending only s and d character together, a variant with its own separate name that most chemistry students never even hear mentioned. The practical partner to hybridization is a rule almost every student learns right alongside it, called valence shell electron pair repulsion, VSEPR for short. The idea is simple enough to explain with party balloons. Tie a handful of balloons together at the stems, and they naturally spread themselves into the same shapes that electron pairs are predicted to take around a central atom, because both are just trying to get as far from each other as the geometry allows. Two balloons point straight opposite each other. Three spread into a flat triangle. Four spread into a tetrahedron, the same shape as methane. It's a useful physical intuition, and it wasn't even the work of one single author. It was proposed independently at least three separate times, once in 1939 by a chemist named Ryutaro Tsuchida in Japan, once in 1940 by Neville Sidgwick and Herbert Powell at Oxford, and worked into its modern, more detailed form in 1957 by Ronald Gillespie and Ronald Nyholm in London. Even the balloon explanation, intuitive as it feels, gets the underlying physics slightly wrong. Ordinary electrostatic repulsion, two negative charges shoving each other away the way two like-charged balloons do, is the easy story to picture. But Gillespie himself argued that the real driving force behind the theory bearing his name is mostly a different, more purely quantum mechanical effect called the Pauli exclusion principle, the identical rule from later in this tour that keeps two electrons from ever occupying the same state. This pushes electron pairs apart from each other far more forcefully than ordinary electric charge alone ever could. The balloon demonstration teaches the right shapes for the wrong underlying reason, a small, easily missed mismatch between a useful classroom prop and the actual physics the prop is supposed to be standing in for. VSEPR explains real measured details that a plain electron pair count misses. Water is bent, not perfectly tetrahedral, with a measured bond angle of 104.5 degrees instead of the ideal 109.5. Because the two lone pairs of electrons on the oxygen sit closer to the nucleus than the bonding pairs do, and they push back harder against everything around them. Ammonia gets the same treatment for the same reason, pyramidal instead of flat. Push the model further and it starts missing badly in ways that are just as well documented as its successes. Xenon hexafluoride ought to be a lopsided pentagonal pyramid according to a strict electron pair count, with the lone pair on xenon shoving everything else out of a perfectly symmetrical shape. Measured directly, it comes out close to a plain, symmetric octahedron instead, with the lone pair barely distorting anything. And chemists still argue over the exact explanation, some pointing to sheer physical crowding among the 6 fluorine atoms, leaving no open space for a lone pair to push into, others pointing to a separate, more exotic effect tied to how heavy elements like xenon start behaving once relativity gets involved. The heavier, alkaline earth metal halides break the model even more plainly. Simple electron counting predicts calcium fluoride, strontium fluoride, and barium fluoride should all be straight, linear molecules. Measured in the gas phase, they're bent, at angles like 145 degrees for calcium fluoride and 108 degrees for barium fluoride. And the accepted explanation involves the metal atoms' inner d orbitals getting involved in the bonding in a way the basic model was never built to account for. Square, flat platinum complexes can't be explained by VSEPR at all, and chemists reach for a completely separate framework, crystal field theory, just to cover that one common shape. Even brand new, artificially made, super heavy elements are predicted to break the pattern their own lighter relatives set. Boron trifluoride is flat and triangular. The much heavier nihonium trifluoride, several rows down the periodic table, is predicted to twist into a different shape entirely, a T shape, purely because of relativistic effects on its electrons that only start to matter once an atom gets that heavy. Chemists formalized the counting itself into a shorthand called the X method, where A stands for the central atom, X stands for each attached atom, and E stands for each lone pair. And the total count of X plus E gives what's called the steric number, the single figure that actually decides the overall geometry. That count can climb well past the 4 bonds carbon usually shows off. Iodine heptafluoride carries a steric number of 7, settling into a shape called a pentagonal bipyramid. A rare rhenium hydride ion manages a steric number of 9, adopting a shape called a tricapped trigonal prism, a geometry no first-year student ever sketches on a homework sheet. And geometries for steric numbers past 9 remain unclear even to specialists, since no ordinary compound built from simple one atom at a time ligands has ever been found to reach that high. Transition metals dodge the whole electron pair counting exercise in a different, quieter way. Lone pairs sitting on a transition metal atom are usually described as stereochemically inactive, meaning they simply don't bother distorting the molecule's shape the way lone pairs on main group atoms like oxygen or nitrogen do. A whole family of related metal complexes built from vanadium, manganese, cobalt, nickel, and zinc, each surrounded by 6 water molecules, all settle into the identical octahedral shape, despite each metal carrying a completely different number of d electrons underneath, a pattern chemists handle with a separate, simplified approach called the Capert model. This just ignores the metals' lone pairs entirely and treats the geometry as though only the attached ligands mattered. It's a second, quieter admission, sitting right next to the first one, that the clean electron pair counting story, taught for simple molecules like water and ammonia, stops being the operative explanation the moment a transition metal walks into the room and gets replaced with a different, purpose-built simplification instead. VSEPR even needs a special patch for molecules carrying a single unpaired electron, since the whole theory is built around counting complete pairs. Chemists handle it by treating one lone unpaired electron as essentially half of a lone pair, weaker at pushing other electrons out of the way than a genuine full pair would be. That patch correctly predicts that the bond angle inside a small family of closely related nitrogen dioxide ions should shrink in careful, measured steps, depending purely on how many extra electrons are crammed in. The positively charged version, sitting at a wide, symmetric 180 degrees. The neutral, uncharged version, bent down to about 134 degrees, and the negatively charged version bent further still to about 115 degrees. Exactly the graded sequence a graded half-strength repulsion effect would predict. The same trick gets applied one atom over to a related chlorine oxide radical. It even fails on its own terms in at least one well-known case. The methyl radical, a carbon atom carrying 3 hydrogens and 1 unpaired electron, ought to be pyramidal by the same logic that makes ammonia pyramidal, since both are built around the same basic electron count. Measured directly, the methyl radical actually sits flat, planar, not pyramidal at all, distorting into the bent shape Vs. EPR predicts only under the gentlest possible push. This makes it the one clean case in this entire corner of the theory, where the electron count and the real measured geometry simply disagree. Pour liquid oxygen over a strong magnet and it clings there, pulled in by the field, the same way iron filings cling to a magnet. That single demonstration breaks the entire picture most students are handed first. A standard Lewis dot structure of an oxygen molecule shows a clean double bond and every electron neatly paired up, and paired electrons shouldn't respond to a magnetic field at all. Oxygen's actual magnetic behavior, called paramagnetism, only happens when a molecule has unpaired electrons sitting around loose. The Lewis structure says there shouldn't be any. The magnet says otherwise every time the demonstration gets run. The explanation needs an entirely different model of bonding, called molecular orbital theory, developed mostly through the 1920s and 30s by a group of physicists and chemists, including Friedrich Hund, Robert Mulliken, John Slater, and John Leonard Jones. The word orbital itself wasn't even coined until Mulliken introduced it in 1932. Instead of picturing electrons as belonging to one specific bond between two particular atoms, the way both Lewis structures and hybridization do, molecular orbital theory spreads electrons across the entire molecule at once, built mathematically by combining every atomic orbital present into a new shared set of molecular orbitals, some of which strengthen the bond called bonding orbitals, and some of which actively weaken it, called antibonding orbitals. Run the actual math for an oxygen molecule, and the diagram predicts exactly 2 unpaired electrons sitting in antibonding orbitals. This is exactly what makes real oxygen stick to a magnet. Explaining that single, easily demonstrated fact was one of the clearest early wins for the whole theory, and it isn't just a demonstration chemists wave their hands at either. Weighing a sample on a sensitive balance, once with a magnetic field switched on and once with it switched off, gives a real quantitative measurement. Since a paramagnetic sample appears to weigh more while the field is active, pulled downward by the same attraction, tugging at the liquid oxygen, and the exact size of that weight change lets a chemist calculate exactly how many unpaired electrons a molecule is carrying, turning a purely qualitative party trick into an actual instrument for testing which bonding theory is right. The whole idea of a chemical bond took a strange, roundabout path to get to that point in the first place. Niels Bohr's own 1913 proposal pictured two bonded atoms held together by a ring of electrons spinning around an axis directly between the two nuclei, a model that borrowed its geometry more from planetary orbits than from anything resembling a modern orbital. Gilbert Lewis, in 1916, threw that picture out and proposed instead that a bond was simply a shared pair of electrons sitting between two atoms. The same year, a separate chemist named Walter Kossel proposed a competing model built entirely around electrons, transferring completely from one atom to another rather than sharing at all, effectively splitting the whole field into an ionic camp and a covalent camp from the very start. It took until 1927 for anyone to actually solve the full quantum mechanics of even the simplest possible bond directly, when the physicist Walter Heitler and the chemist Fritz London worked out a genuine, if approximate, quantum treatment of the ordinary two-electron hydrogen molecule, the calculation that founded the whole valence bond tradition hybridization would later grow out of. A separate calculation published in 1933, more painstaking still, used as many as 13 separate adjustable numbers, later stretched to 54 in an even more refined version, just to match the hydrogen molecule's real measured bonding energy as closely as possible, a brute force approach that convinced much of the chemistry world quantum mechanics really could describe a chemical bond accurately, even though the method itself carried none of the intuitive, hand-drawable picture that made hybridization so appealing to teach in the first place. Underneath all of these theories about bonds sit a whole separate class of much weaker attractions holding entire molecules together, distinct from any actual bond, that chemistry sorts into their own small zoo of specific names. Ordinary molecules with a permanent lopsided charge distribution attract each other through what's called a Keesom force. Molecules with no permanent lopsidedness at all still attract each other weakly through London dispersion forces, a fleeting, constantly flickering imbalance that appears and vanishes as electrons happen to bunch up on one side of a molecule for an instant. Hydrogen bonds, a distinct and noticeably stronger case, form specifically when hydrogen sits attached to a strongly electronegative atom like nitrogen, oxygen, or fluorine, and that lopsided hydrogen then gets pulled toward a spare electron pair on a neighboring molecule, an attraction directly responsible for water's unusually high boiling point compared to other similarly sized molecules that can't form hydrogen bonds at all. A close cousin, the halogen bond, runs the identical trick with a halogen atom playing hydrogen's role instead. None of these forces counts as a real chemical bond by any of the definitions already covered in this tour. And all of them are still strong enough, added up across billions of molecules at once, to be the entire reason water is a liquid at room temperature instead of a gas. Molecular orbital theory and hybridization spent years functioning almost like rival camps inside chemistry, competing to describe the same bonds, before chemists worked out that the two approaches, pushed far enough, are mathematically equivalent descriptions of the same underlying reality, just organized differently. Equivalent doesn't mean equally easy to teach, and it doesn't mean equally accurate for every purpose. Molecular orbital theory is the version that correctly predicts a molecule's ionization energies and its absorption spectrum, the specific wavelengths of light it soaks up, while the older, more intuitive hybridized picture gets those details wrong or needs extra patching to get there. Benzene is the clearest everyday case. Its familiar ring of 6 carbons, usually drawn with 3 neatly alternating double bonds, actually holds 6 electrons, completely smeared out around the whole ring in a pair of donut-shaped orbitals above and below the plane of the molecule, not stuck in any 3 specific bonds at all. Chlorophyll and the pigment beta-carotene get their color for the exact same underlying reason: long stretches of electrons spread out and delocalized across many atoms together. This is why plants are green and carrots are orange in the first place, and it's a molecular orbital explanation, not a Lewis structure one, that actually accounts for it. Robert Mulliken, one of the theory's own founders, pushed the underlying philosophy about as far as it can go, arguing that picturing a molecule as separate atoms held together by a countable number of individual bonds was, strictly speaking, not much more than a convenient approximation, useful for quick calculation, but not a accurate description of what a molecule actually is. In his view, a molecule was better understood as one single, self-contained system built around its own set of nuclei, with the outer portions of every atom's electron cloud belonging jointly to 2 or more nuclei at once, rather than staying loyal to any single parent atom, a description that leaves almost nothing of the tidy ball and stick molecular picture most people carry around intact. Most chemistry students meet hybridization first anyway, years before molecular orbital theory ever gets introduced, if it gets introduced at all outside an actual chemistry degree. The simpler, less accurate picture is the one that sticks, because it's the one taught while intuition is still being built. Molecular orbital theory needs 3 separate conditions satisfied before 2 atomic orbitals are even allowed to combine into a molecular one, and all 3 sound simple but carry real weight. The orbitals need matching symmetry, meaning they have to line up with the same underlying geometric pattern the molecule as a whole follows. They need to physically overlap in space, since 2 orbitals sitting too far apart from each other simply can't interact, no matter how well their symmetry matches, and they need roughly similar starting energy levels because combining a low energy orbital with a much higher energy one barely lowers the system's total energy at all. This means barely any real bonding results. Two helium atoms brought together fail this test almost by definition. Running the full molecular orbital math on a pair of helium atoms gives a bond order of exactly zero, meaning the bonding and anti-bonding contributions cancel completely. And that number matches reality closely enough that a bound helium molecule essentially doesn't exist under ordinary conditions, only showing up as an extremely weak, barely, their pairing detectable in molecular beams, cooled down to almost nothing. Ordinary hydrogen gas, by contrast, comes out with a bond order of exactly 1 and a real measured bond energy of about 436 kilojoules per mole. Strip one electron away to make the hydrogen molecular ion instead, and the bond order drops to 1/2, with a measured bond energy of only about 171 kilojoules per mole, a far weaker bond, exactly as the simple bond order arithmetic predicts. The very first fully rigorous quantum mechanical description of any chemical bond at all, worked out mathematically in 1927 by the Danish physicist Øyvind Burau, was built on exactly that stripped down hydrogen ion, a single electron holding two nuclei together, because it was the only bonded system simple enough for the full mathematics of the era to actually solve without approximation, even after conceding that molecular orbital theory is the more accurate of the two pictures. Chemists still don't agree on a single way to draw the resulting orbitals for anything with more than one bond or more than one lone pair. The smeared out, delocalized orbitals molecular orbital theory naturally produces can be mathematically converted with no loss of accuracy back into a set of localized orbitals that look almost exactly like Pauling's original hybrids, since the underlying total energy and electron density of the whole molecule come out identical either way for a molecule sitting in its ground state. For molecules with several bonds or several lone pairs in one go, chemists then split again over which localized picture to actually use. Most textbooks describe double and triple bonds using a separate sigma and pi framework, one straight bond plus one or two looping side bonds, while describing multiple lone pairs on the same atom using a different so-called equivalent or bent bond picture instead, mixing and matching two different stylistic conventions depending on which part of the molecule is being discussed, with a smaller number of chemists preferring to apply the sigma pi framework consistently across both cases instead. Both conventions are mathematically legitimate. Neither is uniquely correct. Which one shows up in a given textbook comes down to which tradition the author happened to be trained in. One more case of chemistry running two competing pictures side by side without ever forcing either one out. Benzin's ring gets its own extended treatment because the standard classroom drawing of it is such a widely repeated piece of chemistry folklore. August Kekule proposed the ring shape in 1865. 6 carbon atoms arranged in a hexagon with alternating single and double bonds circling around. And the drawing was good enough at explaining benzene's chemical behavior that it stuck immediately and never really left. It's still the first drawing nearly every organic chemistry student gets handed. The alternating bonds aren't real, and chemists have known that for a very long time. Every single one of the 6 carbon-carbon bonds in an actual benzene molecule measures out to the exact same length, sitting right in between a normal single bond and a normal double bond, not alternating between the two lengths the classic drawing implies. Chemists represent this by drawing two separate Kekulé structures side by side with a double-headed arrow connecting them, which is a specific, deliberate warning sign in chemical notation. That arrow doesn't mean the molecule flips back and forth between the two drawings over time. It means neither drawing is real on its own, and the true structure is a blend called a resonance hybrid that only exists as the average of the two hypothetical pictures. Erich Huckel worked out the real quantum mechanical explanation in 1931, the same era that gave chemistry both hybridization and molecular orbital theory. By separating a molecule's bonding electrons into two distinct types for the first time, the ordinary bonds running directly between atoms and a separate set of electrons free to move above and below the plane of the ring. In benzene, 6 of those free electrons end up smeared evenly around the whole ring at once, which is the real reason all 6 bonds come out identical, and the reason the ring is dramatically more stable and less reactive than a plain, non-aromatic ring of the same size would be. Huckel's own rule for predicting which rings get this special stability, now taught as a simple head count, 4 times some whole number plus 2 delocalized electrons in the ring, works cleanly for flat, single rings and starts breaking down almost immediately outside that narrow case. A related molecule called guanidinium is unusually stable and unusually good at holding onto extra protons, even though it has no ring in it at all. And chemists coined a separate term, Y-aromaticity, to try to explain why, an idea the research literature itself describes as controversial instead of settled. Rings that ought to be stable by the electron count sometimes twist themselves out of flatness, specifically to dodge the instability flatness would cause. The way cyclooctatetraene physically buckles out of a flat ring shape to avoid becoming what chemists call anti-aromatic, actively destabilized by the very same rule that stabilizes benzene. Aromaticity has even turned up somewhere. Carbon has no business claiming credit for it at all. Small clusters built purely from aluminum atoms, with no carbon anywhere in the structure, have been shown to carry the exact same kind of delocalized ring-stabilizing electron behavior that benzene relies on, a purely metallic version of aromaticity that would have sounded like a contradiction in terms to 19th century chemists, who assumed the whole property belonged exclusively to a narrow family of carbon-based, sweet-smelling compounds. Even the word aromatic is a historical accident nobody ever bothered to fix. A chemist named August Wilhelm Hofmann first used the term in 1855 for compounds built around the same basic ring structure as benzene, mostly because early examples of the class happened to smell pleasant. Most aromatic compounds, including benzene itself, don't have any particularly strong or pleasant smell at all, and plenty of strong smelling organic compounds, the terpenes that give pine trees and citrus fruit their scent, aren't aromatic in the chemical sense whatsoever. The name describes a coincidence from one 19th century chemist's nose, not any real property of the molecules, and it's still been the official term for this entire branch of chemistry for over 170 years anyway. Chemists have even pushed the whole concept of aromaticity to its outer edge on purpose, building strange test case molecules called cyclophanes, specifically to see exactly where the rule finally breaks. Aromaticity turns out to matter for reasons that go well past chemistry classroom trivia. 4 of the 20 amino acids that build every protein on Earth are themselves aromatic. All 5 of the bases spelling out the genetic code in DNA and RNA are aromatic rings too. Heme, the molecule that lets blood carry oxygen, and chlorophyll, the molecule that lets plants capture sunlight, both build their function around a much larger aromatic ring system stretched across more than 20 delocalized electrons, all at the same time. This means the same electron smearing trick sitting underneath a benzene molecule is also, one way or another, sitting underneath most of the machinery that keeps a living cell running. Industrially, benzene and its close relatives, toluene and the 2 common forms of xylene, get produced worldwide at a scale north of 35 million tons a year, refined out of crude oil or coal tar, and then built into everything from polyester fabric to nylon to plain styrene plastic. A enormous slice of the modern chemical industry resting on a molecule whose defining textbook drawing has been technically inaccurate since before most of that industry existed. Chemists even have a direct physical way to catch aromaticity in the act, rather than just inferring it from stability and bond length. Delocalized electrons circling an aromatic ring when the whole molecule sits inside a strong magnetic field generate their own small looping electric current called a ring current that pushes back against the outside field in a specific, measurable way. That ring current shows up clearly in nuclear magnetic resonance spectroscopy, shifting the signal from hydrogen atoms sitting around the outer edge of an aromatic ring noticeably further than an equivalent hydrogen on a non-aromatic molecule would show. This gives chemists a genuine, direct, instrumental test for aromaticity instead of just a stability argument built entirely on second-hand reasoning. Aromaticity isn't even a single whole molecule property in bigger structures, which trips up the assumption that a molecule is simply aromatic or not. Phenanthine, built from 3 fused benzene-style rings joined together, has a central ring that measures out as noticeably less aromatic and noticeably more chemically reactive than the two outer rings flanking it, even though all three rings look identical on a casual glance at the drawing. Chemists have had to build a whole separate vocabulary just to describe that split global aromaticity for measurements that describe a molecule's entire delocalized system taken together, and local aromaticity for describing the character of one specific ring buried inside a larger structure, since the two numbers disagree with each other often enough to matter. An even stranger theoretical variant, called Mobius aromaticity, predicts that a ring of delocalized electrons, given a single half twist, the same twist that turns an ordinary paper loop into a one-sided Mobius strip, should follow the exact opposite electron counting rule from ordinary flat aromatic rings, stable with electron counts that would destabilize a normal ring, and vice versa. As late as 2012, chemists still had no confirmed, undisputed example of a genuine Mobius aromatic molecule ever actually synthesized in a lab. A purely theoretical prediction sitting in textbooks for decades, with the real experimental proof still pending. A related idea called homoaromaticity stretches the whole concept even further, describing molecules where the ring of delocalized electrons is physically interrupted by one ordinary, non-participating carbon atom sitting in the middle of the loop, breaking the continuous ring. Any strict reading of Huckel's rule would require, and yet the molecule still measurably picks up real aromatic style stability anyway, as though the electrons found a way to skip past the gap and keep circulating regardless. So even the shapes and the bonds taught first turn out to be simplified stand-ins for something messier underneath. The single most confusing idea in chemistry isn't about atoms at all, though. It's about energy, and it trips up almost everyone in exactly the same place, for reasons researchers who study chemistry education have actually gone and documented. Chemistry students spend an enormous amount of time on entropy, and most of them come away with the wrong idea of what it actually measures, not because they weren't paying attention, but because the standard shorthand for entropy is itself misleading, and the people who study how chemistry gets taught have written about this directly. The usual shorthand calls entropy a measure of disorder. That word gets attached to entropy in textbook after textbook, and it's a bad word to use because disorder and chaos means something close to the opposite of equilibrium in ordinary, everyday English. And researchers studying student misconceptions have flagged that exact mismatch as a real source of the widespread confusion around the concept, not just an unfortunate simplification that happens not to matter. Here's where the word actually came from. Rudolf Clausius named the quantity in 1865, pulling it from the ancient Greek word for transformation, and he built it on purpose to echo the word energy, because he thought the two ideas were close enough in physical importance to deserve names that sounded like siblings. He preferred going to old, dead languages for big scientific names, specifically so a word would carry the same sense no matter which living language a scientist happened to be reading in. One later physicist, reflecting on the choice, pointed out that Clausius had, in effect, built a word that everybody could agree meant exactly nothing. This was sort of the joke buried inside a very serious piece of naming. Before landing on entropy, the concept had already gone through other names entirely. A Scottish engineer named William Rankine called an early version of it the thermodynamic function, or heat potential, back in 1850. Clausius himself first described it as transformation content before settling on the shorter Greek-rooted word instead. The rigorous version of entropy, the one that actually explains what the word is doing, has two separate faces, and both grew out of careful 19th century physics rather than casual metaphor. The classical macroscopic version, developed by Clausius directly, defines a small change in entropy as a small amount of heat moved into a system during a reversible process, divided by the temperature at which that heat moves. That version comes straight out of studying steam engines and the Carnot cycle, the theoretical heat engine that sets the outer limit on how efficient any real engine can ever be. The second, statistical phase of entropy, developed by the Austrian physicist Ludwig Boltzmann through the 1870s, defines entropy in terms of counting. Take any large collection of atoms sitting in some observable overall state, a certain temperature, a certain pressure, a certain volume, and ask how many different microscopic arrangements of the individual atoms could all produce that exact same observable state. Entropy is a logarithm of that count, scaled by a single fixed number now called the Boltzmann constant. A state with more possible hidden arrangements underneath it carries more entropy. That's what the equation says. Nothing in either the classical or the statistical definition mentions messiness, spilled paperwork, a teenager's bedroom, or any of the visual shorthand entropy usually gets illustrated with. A newer way of teaching the idea, pushed hardest by the physical chemist Peter Atkins in his own textbooks, drops the word disorder altogether and talks about dispersal instead, the notion that a spontaneous change spreads energy or matter or both out over a wider range of possibilities than it started in. That framing survives contact with real chemistry a lot better than disorder does. It explains why a hot object and a cold object drift toward the same middle temperature when they touch. Since the total energy spreads itself out over more of the possible microscopic arrangements once it's no longer stuck concentrated in one place. It explains why a gas expands to fill a container instead of staying crammed in one corner. It just doesn't produce the vivid, wrong mental picture of tidiness collapsing into mess that the word disorder drags along with it. Textbooks themselves can't even agree on one sentence to define entropy with, which is its own small, quiet echo of the acid problem from earlier. One common definition calls entropy a measure of energy dispersal at a given temperature. Another calls it a measure of disorder, or of how much of a system's energy has become unavailable to do useful work. A third calls it, more narrowly, a measure of thermal energy per unit of temperature that can't be turned into useful work. A fourth, Boltzmann's own framing, calls it a count of the possible microscopic arrangements consistent with what can actually be measured about a system. All four show up side by side inside the very same reference material. A chemistry student is likely to be handed, with no flag raised, that these are four different lenses on one number rather than four restatements of one identical idea. At least one physicist has tried to rescue the disorder framing instead of abandon it outright. Peter Landsberg proposed, back in 1984, an actual mathematical formula for order and disorder built by borrowing tools from information theory, treating a system's disorder as a ratio between how much of its behavior is unpredictable and how much information it could theoretically hold. In total, the attempt is a serious, careful piece of physics, and it hasn't replaced Boltzmann's plain microstate count as the field's actual working definition of entropy. This is worth noting for what it says about the state of the whole conversation, that even a formal, rigorous attempt to make the word disorder mean something precise still sits as a side proposal, not the standard. Decades later, the second law of thermodynamics, built on top of all of this, says the total entropy of an isolated system left alone does not decrease over time. Confusingly, that's a statistical statement dressed up to sound like an absolute one. Because entropy counts probability, a spontaneous decrease in entropy inside an isolated system isn't actually forbidden by the underlying physics at all. It's just staggeringly, overwhelmingly unlikely, to the point where nobody has ever observed it happen at any scale worth mentioning. And the second law gets taught and used as though it were an ironclad rule, because for any real collection of atoms, it might as well be one. That same rule is also the reason nobody has ever managed to build a genuine perpetual motion machine, a device that runs forever on no outside energy at all. Every real attempt eventually loses ground to entropy. Push the same logic out to the largest possible scale, and cosmologists have speculated since the 19th century about a heat death of the universe, a distant future state where energy has spread out so completely and evenly that no further useful work can be extracted from anywhere ever again. Nobody treats that prediction as settled science, and the role entropy actually plays in cosmology has stayed a disputed question among physicists going all the way back to Boltzmann's own lifetime. Some newer analyses of an expanding universe suggest the maximum possible entropy the universe could ever hold is climbing even faster than its actual entropy is, opening up a widening gap between the two rather than closing it. This would push any eventual heat death further away with time instead of nearer, the opposite of the simple picture most popular explanations settle for. Black holes complicate the question even further, since Jacob Bekenstein and Stephen Hawking showed that a black hole carries more entropy than any other object of the same physical size could possibly hold, entropy that scales with the surface area of the black hole rather than its volume, a strange result on its own that most working physicists still haven't fully reconciled with the rest of thermodynamics. It's a long, unsettled extrapolation of the same second law that governs a cooling cup of coffee, stretched out to a timescale nobody will ever be around to check. Entropy shows up in unexpected corners once the statistical, counting based version of the idea gets taken seriously as a general tool instead of as a narrow chemistry concept. A 2011 study published in the journal Science tried to estimate humanity's entire technological capacity to store and move information using the exact same entropy-based mathematics chemists use for microstates, treating a hard drive full of data the same way a physicist treats a container of gas. By that measure, the study estimated the world's total data storage capacity grew from around 2.6 exabytes in 1986 to around 295 exabytes by 2007. And the capacity to move information across two-way telecommunication networks grew even faster over the same stretch, from around 281 petabytes a year up to around 65 exabytes a year. None of that has anything to do with chemistry directly, but the underlying entropy math, counting hidden possible arrangements and comparing them against what can actually be observed, is identical. This is a real hint that entropy was never a narrowly chemical idea to begin with. Just a piece of mathematics chemistry happened to need first. Biologists have started borrowing the same math to study genetics too, measuring the entropy of a DNA sequence to tell coding regions apart from non-coding ones and to help reconstruct evolutionary trees by treating the genetic distance between two species as an entropy calculation in its own right. One more field reaching for a tool chemistry only ever borrowed from physics in the first place and never actually owned. Mixing itself turns out to be its own small, specific source of entropy, separate from temperature or pressure changing at all. Combine two different substances that already sit at the same temperature and the same pressure so that no heat and no mechanical work pass between them in the process, and the total entropy of the combined system still goes up, purely from the act of mixing itself, because each individual particle now has access to a larger total volume to wander through than it had while confined to its own separate container. That single fact, entropy of mixing, is part of why oil and water refusing to combine is the surprising case chemically, not the expected one, since almost any two substances that could mix freely would gain entropy by doing so. And it takes a specific, strong reason, like water's own network of hydrogen bonds, rejecting oil's non-polar structure, to overcome that natural pull toward mixing and keep the two liquids apart. Even reporting an entropy value carries its own small fork in the road, since entropy scales with the sheer size of whatever's being measured. More material simply carries more entropy. This makes a raw entropy number close to meaningless for comparing two different amounts of two different substances. Chemists get around that by reporting entropy per unit of something instead, either specific entropy, entropy divided by mass, or molar entropy, entropy divided by the amount of substance measured in moles. And a table of standard values needs to specify plainly which of the two it's using, since mixing the two up in a calculation produces a number that's wrong by whatever factor separates a substance's molar mass from one. Chemical engineers designing real industrial equipment have to track entropy in an even messier form still, since a working factory reactor isn't a sealed textbook system at all and has heat, mechanical work, and actual streams of matter all crossing its boundaries continuously while it runs. Every one of those flows carries its own entropy, contribution in or out, along with it, mass flowing in, bringing its own entropy with it, the way a person walking through a doorway brings their own body heat into a room. And engineers have to add all of those separate contributions together, plus whatever fresh entropy the reaction itself is generating internally, just to describe one running piece of equipment properly. A far messier bookkeeping problem than the single, static, sealed flask entropy value taught in an introductory course ever has to deal with. Inside an actual chemical reaction, entropy doesn't act alone. What decides whether a reaction runs forward on its own is a balance between the heat a reaction releases or absorbs and the entropy change it causes, both in the reacting substances themselves and in everything around them. Getting that balance right and boiling it down to a single number is exactly the problem a different scientist solved a few years after Clausius. And that number turns out to be the second most misunderstood idea in the entire subject. Josiah Willard Gibbs worked the problem out through the 1870s, publishing his first major paper on it in 1873 and calling the quantity, in his own writing, available energy, before later scientists shortened and renamed it Gibbs free energy in his honor. The formula itself is short. Gibbs free energy equals enthalpy, essentially the total heat content of a system minus temperature multiplied by entropy. What chemists actually care about almost every time is the change in that quantity from the start of a reaction to the end, written as delta G. This comes out to the change in enthalpy minus temperature multiplied by the change in entropy. If that number comes out negative, chemists call the reaction spontaneous, and that single word causes more confusion faster than almost anything else in the vocabulary of chemistry, because it doesn't mean what it sounds like it means in ordinary conversation. Spontaneous, in this specific technical sense, has nothing to do with speed. It has nothing to do with a reaction happening the instant the reactants get combined, and it has nothing to do with any sense of eagerness or tendency on the part of the molecules involved. It's purely a comparison between two fixed points, the starting arrangement of a system and the ending arrangement, with the path between the two and the amount of time that path takes, left completely out of the calculation. Gibbs free energy is what mathematicians and physicists call a state function, meaning its value depends only on where a system starts and where it ends, never on the road taken to get there. A reaction can be thermodynamically spontaneous by every measure chemistry has and still take years, decades, or in some real cases, close to forever to actually happen. Because how fast a reaction proceeds is governed by an entirely separate branch of the subject called chemical kinetics, built around ideas like activation energy, rate laws, and the specific step by step mechanism a reaction has to pass through, none of which appear anywhere in the Gibbs free energy equation at all. Thermodynamics answers whether a reaction is allowed to happen given enough time and no obstacles in the way. Kinetics answers whether it happens on any time scale anybody could ever actually witness. Chemistry teaches both words, spontaneous and reaction rate, close together in the same course, and plenty of students walk out treating them as roughly the same idea, when they actually describe two questions that don't even share an equation. Kinetics has its own habit of disobeying the balanced equation, sitting right above it on the page, in a way that mirrors the same trap waiting inside equilibrium later in this tour. Take the reaction between carbon monoxide and nitrogen dioxide, producing carbon dioxide and ordinary nitric oxide. A naive reading of the balanced equation might guess the reaction rate depends on the concentration of both gases equally. Measured directly, the rate depends only on the square of the nitrogen dioxide concentration, with the carbon monoxide not showing up in the rate expression at all, because the real reaction actually happens in two separate hidden steps. Two nitrogen dioxide molecules first colliding slowly to form an intermediate, and that intermediate then reacting with carbon monoxide almost instantly right afterward. The slow first step alone sets the pace for the entire reaction, which is why the fast second step and the carbon monoxide it consumes disappear from the rate law entirely, even though carbon monoxide is sitting right there in the original balanced equation. A more elaborate case, the breakdown of acetaldehyde into methane and carbon monoxide, follows an experimentally measured rate that depends on concentration raised to the power of 3/2, a fractional exponent that has no obvious connection to any whole number coefficient in the overall equation at all, and only makes sense once the reaction gets broken down into a full four-step chain mechanism, complete with free radical intermediates being created, consumed, and destroyed at carefully matched rates underneath the hood. A chain mechanism like that runs through its own small, named vocabulary of stages, an initiation step that first breaks a stable molecule into unstable fragments, propagation steps, where one reactive fragment hands its instability off to a fresh molecule while creating a new fragment of its own, and a termination step where two of those loose reactive fragments finally collide with each other and cancel out, ending the chain. Some chains pick up a branching step along the way, where one reactive fragment somehow spawns more than one new fragment instead of just one. And it's exactly that kind of branching that turns an ordinary, well-behaved chain reaction into an explosion, once it runs away from itself faster than it can be controlled, None of that machinery is visible anywhere in the tidy one-line equation a student first learns to balance. Proving a hidden mechanism like that actually happened the way chemists claim, rather than just fitting the numbers after the fact, takes real detective work, since the individual steps almost never last long enough to observe directly. Chemists lean on a whole toolkit of indirect evidence instead, measuring how the reaction rate shifts as temperature changes to work out an activation energy, watching for short-lived intermediates with fast spectroscopic equipment, swapping ordinary atoms for heavier isotopes, and checking whether the reaction slows down as a result, and running so-called crossover experiments, deliberately mixing labeled and unlabeled versions of a reactant together and checking whether the labels end up scrambled or preserved in the final product, each one a different, indirect way of catching a process too fast and too small to ever watch happen directly. For large, messy systems, a burning flame or an ionized plasma working out a complete mechanism by hand stops being realistic at all, since a real flame runs through dozens or hundreds of individual elementary steps simultaneously, and chemists studying combustion routinely fall back on computer modeling and group additivity methods, essentially educated approximation techniques for estimating a molecule's reaction behavior from the known behavior of its smaller structural pieces, whenever the actual, complete rate data for a step simply doesn't exist in the published literature yet. Even mechanism itself, the supposedly rigorous step-by-step foundation kinetics is built on, turns out to run on approximation and informed guesswork the moment a real system gets complicated enough. The temperature term inside the equation does real, specific work, and it produces counterintuitive results depending on the sign of the enthalpy change and the sign of the entropy change. When a reaction both absorbs heat and increases entropy, it only turns spontaneous once the temperature climbs high enough for the entropy term to outweigh the enthalpy term. So the exact same reaction can sit non-spontaneous at room temperature and spontaneous at a higher one, with nothing about the chemicals themselves changing at all. When a reaction both releases heat and decreases entropy, the relationship flips, and the reaction is only spontaneous below some cutoff temperature, turning non-spontaneous again once things get too warm. Only two of the four possible combinations avoid this temperature dependence entirely. A reaction that releases heat and increases entropy at the same time is spontaneous at every temperature, no exceptions. A reaction that absorbs heat and decreases entropy at the same time is never spontaneous at any temperature, no matter how the conditions get adjusted. Two of the four cases are fixed. Two of the four flip depending on how hot or cold the surroundings happen to be. This means the single most basic question in chemistry, whether a given reaction runs forward or not, sometimes doesn't even have a fixed yes or no answer until somebody specifies a temperature. Gibbs free energy also reaches directly into the equilibrium constant, the number that describes exactly where a reversible reaction settles once it stops shifting through a clean logarithmic relationship. Standard Gibbs free energy change equals negative the gas constant times temperature times the natural logarithm of the equilibrium constant. That equation is the actual bridge between two topics usually taught as though they belong to separate chapters of the textbook. And it means every equilibrium constant a chemist has ever measured is secretly also a measurement of a Gibbs free energy change run through a logarithm. None of these Gibbs free energy numbers are absolute in the first place either. This is easy to miss since they get reported as plain fixed figures in a reference table. Every element in its own ordinary natural form, plain oxygen gas, solid graphite, gets assigned a standard Gibbs free energy of formation of exactly zero by simple convention, a deliberately chosen reference point instead of a measured absolute zero of energy, the same basic trick as measuring a mountain's height from sea level rather than from the actual center of the earth. Every other Gibbs free energy value a chemist ever reports is really a difference measured against that one arbitrary, agreed upon 0 point. This works perfectly well for comparing reactions against each other and would mean essentially nothing as a absolute number on its own. The name itself carries one more small, telling piece of confusion. The International Union of Pure and Applied Chemistry recommended dropping the word free from the name entirely back in 1988 at a meeting called specifically to standardize international scientific terminology, preferring the plainer Gibbs energy instead, on the reasoning that free oversells what the number actually measures. Since it's only free for a narrow category of work other than simple pressure and volume changes, not free in any general sense a non-specialist would assume. Almost 4 decades later, the recommendation still hasn't been universally adopted, and most working chemists, most textbooks, and this very explanation still default to calling it free energy anyway, in mild, ongoing defiance of the field's own naming authority. Gibbs free energy also has a close sibling most students meet in the very same unit and easily confuse it with, called Helmholtz free energy, and the difference between the two comes down entirely to which condition gets held fixed while a reaction happens. Gibbs free energy governs reactions run at constant pressure, the ordinary situation for almost any reaction happening in an open flask or a living cell exposed to the atmosphere. Helmholtz free energy governs the same kind of question for a reaction run instead at constant volume, sealed inside a rigid container where pressure is free to change, but the container itself can't expand or contract. The two quantities agree closely for reactions that don't involve much change in volume and can diverge noticeably for reactions that do, particularly ones involving gases, and picking the wrong one of the two for a given real setup produces a wrong answer, not just an imprecise one, about whether a given reaction is actually favorable under the specific conditions it's really running in. Gibbs himself introduced the whole concept graphically instead of algebraically, which is easy to forget given how the idea gets taught today as a bare equation. His first major paper on the subject, published in 1873, plotted a substance's state using only entropy and volume as the two axes. A second paper, published later that same year, added a third axis, energy, turning the whole picture into a three-dimensional surface. The following year, the physicist James Clerk Maxwell, working off Gibbs's published figures, built an actual physical, three-dimensional plaster model of that surface for a fictional water-like substance, sculpting stability, instability, and phase change directly into solid plaster, so the shape of the mathematics could be picked up and turned around in someone's hands. Gibbs' free energy, in other words, started life as a literal object on a shelf before it ever became the single, flat, algebraic line most chemistry students meet first. The equation also reaches directly into electrochemistry, tying Gibbs' free energy straight to the voltage produced by a battery. The Gibbs free energy change of a reaction happening inside an electrochemical cell equals the negative of the number of electrons transferred times the Faraday constant times the cell's own measured voltage. This means a battery's voltage is, underneath the engineering, a direct readout of a Gibbs free energy change happening in real time as the cell discharges. Rearranged slightly, that same relationship becomes the Nernst equation, the formula used to predict exactly how a cell's voltage shifts as the concentrations of the chemicals inside it change while it runs down, connecting the same energy accounting from earlier in this tour directly to something as ordinary as how a flashlight battery slowly loses power over the course of an afternoon. This is the one. Ask researchers who study how chemistry actually gets misunderstood, which single topic causes the most trouble, and chemical equilibrium comes out on top repeatedly, described in the literature as a root cause confusion rather than an isolated one, because a shaky grip on equilibrium doesn't just cost a student points on one test, it wrecks acid-base chemistry, redox chemistry, and solubility later on, since all three lean on the same underlying idea, and equilibrium is supposed to teach first. Part of the trouble starts with the word itself. Equilibrium sounds like stillness. It sounds like a reaction that has stopped, settled, gone quiet. That's exactly backward. Nothing has stopped. A reaction sitting at chemical equilibrium hasn't stopped at all. It's constantly running forward and backward at the same time at exactly matched rates, so that the measurable concentrations of everything in the mixture hold steady, even though individual molecules are reacting every single moment. Dissolve acetic acid in water and let the mixture settle into equilibrium. And at the molecular level, a proton is still hopping right then off one particular acetic acid molecule and onto a nearby water molecule, turning that acetic acid into an acetate ion and that water into a hydronium ion, while somewhere else in the same beaker, A different hydronium ion is handing a proton back to a different acetate ion, reversing the same reaction in the opposite direction. Chemists call this dynamic equilibrium, specifically to head off the wrong impression, and the ordinary static sounding word equilibrium survives anyway as the everyday shorthand, still implying to a beginner reading it cold that the whole system has simply stopped doing anything. The idea traces back to a French chemist named Berthollet, who noticed in 1803 that some chemical reactions run in reverse under the right conditions, instead of going only one way to completion. More than 60 years later, in 1865, two chemists named Cato Goldberg and Peter Waage built that observation into a formal rule called the law of mass action, proposing that the forward reaction rate and the backward reaction rate each depend on the concentrations of the substances reacting, raised to powers matching their coefficients in the balanced equation, and that at equilibrium those two rates lock together and become equal. The ratio between the two rate constants involved is what chemists now call the equilibrium constant, usually written K, and it's correctly treated as one of the single most useful numbers in all of chemistry, since it tells exactly how far a reaction runs before it settles, whether it favors piling up products or barely budging off the starting materials. Chemists have their own casual shorthand for describing where that balance point sits, calling an equilibrium that ends up mostly turned into products one that lies far to the right, following the way a reaction equation gets written left to right on the page, and calling an equilibrium that barely budges off its starting materials one that lies far to the left, spatial language borrowed for a balance point that has nothing to do with actual physical direction at all. K itself only describes the one fixed destination a reaction is heading toward, not where the reaction actually happens to be sitting at any given moment along the way. This is why chemists track a second closely related number called the reaction quotient, built with the identical formula as K but calculated from whatever concentrations are actually present right now, before the system has necessarily settled. When the reaction quotient and the equilibrium constant come out equal, the system has arrived at equilibrium. Whenever they don't match, the gap between the two numbers is exactly what tells a chemist which direction the reaction still needs to shift, and by how much. A live, moving comparison against a single, fixed target. The plain word equilibrium alone never quite manages to convey, since one number is a fixed destination and the other is wherever the reaction actually happens to stand right now. Here's the twist that almost never gets mentioned once the equilibrium constant gets introduced. The law of mass action, the very equation that defines K in the first place, is only strictly, rigorously true for a reaction that happens in one single step, what chemists call a concerted, one-step reaction passing through a single transition state. Most real reactions don't work that way. They proceed through multiple elementary steps in sequence, intermediates forming and breaking down along the way. And for reactions built like that, the rate equation frequently doesn't follow the overall balanced equation's coefficients at all. Certain well-documented reaction types, a category of substitution reaction chemists label SN1, or the classic reaction between hydrogen gas and bromine gas to form hydrogen bromide. Both follow rate laws that break cleanly from what the law of mass action alone would predict. Individual reaction steps get their own separate label for how many molecules actually collide at once, called molecularity, and it turns out the number essentially never climbs past 2 in practice. A step involving one molecule alone is unimolecular. A step involving 2 colliding molecules is bimolecular. A step needing 3 separate molecules to collide at the exact same instant is termolecular, and steps needing more than 3 practically never happen at all, since the odds of 4 or more separate molecules arriving at the same point in space at the same moment by ordinary random collision alone are low enough to rule the possibility out entirely. Every complicated multi-step mechanism this tour has already touched on, the nitrogen dioxide and carbon monoxide reaction, the acetaldehyde chain breakdown, is built entirely out of these 1 and 2 molecule collisions stacked in sequence. Never anything grander, because chemistry at the molecular level can't manage a bigger pileup than that. Equality between the forward and backward reaction rates remains a real necessary condition for any system actually sitting at equilibrium. It just isn't by itself a full explanation of why equilibrium happens at all. And the tidy classroom formula, taught as though it derives directly and universally from first principles, is, in the fine print, an approximation that only holds cleanly for the simplest possible case. There's a second trap sitting right next to the first one, and it's arguably more dangerous because it looks identical to real equilibrium from the outside. A mixture can sit there, apparently unchanging, concentration steady, nothing visibly happening, and still not actually be at equilibrium at all. Chemists call this a metastable mixture, and the difference between metastable and truly at equilibrium is invisible unless someone already knows to look for it. Mix sulfur dioxide gas with oxygen gas, and the 2 will happily sit together, seemingly forever, without turning into sulfur trioxide. Not because the reaction is unfavorable, but because there's a kinetic barrier blocking it, an energy hump the molecules can't easily climb over on their own. Add the right catalyst, the same one industrial chemists use in what's called the contact process, and the reaction suddenly proceeds, reaching the equilibrium it was always thermodynamically entitled to reach the whole time, just unable to get there unassisted. Carbon dioxide dissolving into water to form bicarbonate ions runs the same trick in reverse. Left to itself, that reaction is slow enough to matter industrially and biologically. Add the enzyme carbonic anhydrase, found throughout the human body specifically to speed this exact reaction up, and the same transformation becomes almost instantaneous. In neither case does the catalyst move where the equilibrium sits or change the value of the equilibrium constant at all. It only removes the kinetic roadblock standing between the mixture and the equilibrium position it was heading toward the entire time. This means the same lesson from Gibbs' free energy shows up again here from a completely different angle. Whether something is thermodynamically allowed to happen and whether it actually happens on any observable timescale keep turning out to be two separate questions answered by two separate branches of the same subject, and equilibrium chemistry sits exactly on the seam between the two. Once a reaction is confirmed to be at equilibrium, describing exactly where it sits gets complicated fast in ways that rarely make it past the simplest textbook cases. Pure solids and pure liquids taking part in a reaction don't even appear in the equilibrium constant expression at all, since their concentrations in the mathematics chemists use are treated as a fixed value of 1, no matter how much of the solid or liquid is physically present. The plain concentration values plugged into an equilibrium constant formula in an introductory class are themselves a simplified stand-in for something messier in a pattern that ought to feel familiar by now. Rigorously, an equilibrium constant is defined using a quantity called activity rather than raw concentration, a number meant to capture how a dissolved substance actually behaves chemically instead of simply how much of it is physically present. An activity only equals plain concentration in the idealized limit of an infinitely dilute solution, where every dissolved particle is far enough from every other one to ignore them completely. Real solutions, sitting anywhere short of that idealized limit, have dissolved particles constantly interacting with and interfering with each other, which pulls their real activity away from their raw concentration by an amount that grows the more crowded and concentrated the solution gets. Introductory chemistry teaches the concentration version because it's close enough to correct for dilute solutions and vastly easier to measure directly, and sets aside the activity version, the one the actual rigorous definition is built on, for a more advanced course later. Real equilibrium constants measured in the lab depend on ionic strength, the total concentration of charged particles floating around in a solution. This means a published value measured under one set of conditions can be flatly wrong if it's applied to a solution with a different ionic strength without adjustment first. And chemists sometimes handle this by measuring K across a whole series of different ionic strengths and mathematically extrapolating all the way down to a solution with essentially none, arriving at what gets called, almost as a private joke inside the field, a thermodynamic equilibrium constant, just because it describes a condition that barely exists in any real laboratory solution. The equilibrium constant also shifts with temperature, following a relationship called the Van't Hoff equation, and it looks, on paper, like a tempting shortcut for measuring a reaction's enthalpy change simply by watching how K moves as the temperature changes. In practice, chemists are directly warned off relying on that shortcut. Since the method compounds errors badly enough, propagating small measurement uncertainties into large ones through the calculation that the resulting enthalpy values usually come out too unreliable to trust. A rare case in this whole subject where a clean textbook derivable equation gets flagged in the very literature that derives it as a bad idea to actually use in a real laboratory. Working out the actual composition of a mixture at equilibrium, once several reactions are happening simultaneously and several equilibria are interacting, generally can't be solved with one clean equation at all. Chemists fall back on one of three separate approaches depending on the problem: manipulating known equilibrium constants algebraically until the unknown concentrations pop out, directly minimizing the total Gibbs energy of the whole system numerically until it settles at its lowest point, or setting up a full system of mass balance equations that just track every atom of every element through the mixture and solve everything simultaneously. None of the three methods is simple by hand for anything beyond the most basic textbook example, and real chemists working real mixtures with more than 2 or 3 reacting species usually solve the resulting equations with a computer rather than a pencil. This is a fairly large admission buried in the chemistry literature that the topic sold to first-year students as a clean algebra problem is, in its full form, not one at all. Equilibrium chemistry, once it leaves the classroom, ends up running an enormous stretch of the physical world in the background. Rocket engines rely on gas phase equilibria inside their combustion chambers. Atmospheric chemistry, the whole layered system of reactions holding the ozone layer and the general composition of the air together, is built out of interlocking equilibria. Hemoglobin picking up oxygen in the lungs and releasing it again out in the body's tissues is an equilibrium process on its own, shifting back and forth depending on local oxygen concentration, exactly the way Le Chatelier's principle would predict. Chelation therapy, the same treatment already mentioned for penicillamine, and the contrast agents used in medical MRI scans both work by exploiting metal ligand equilibria deliberately, tuning a binding constant until a specific metal ion gets pulled out of the body, or lit up clearly on a scan on command. Some reactions don't settle into equilibrium smoothly at all. A handful of unusual oscillating reactions approach their final equilibrium point, the way a dropped weight settles on a spring, overshooting and swinging back repeatedly in a damped oscillation. The concentration of one dye-colored intermediate, visibly pulsing back and forth in the same reaction flask for minutes at a time before finally calming down to a fixed, boring endpoint. Even the vocabulary used to describe binding strength in biochemistry sprawls out into its own small pile of near synonyms: stability constant, formation constant, binding constant, affinity constant, association constant, dissociation constant, each one describing essentially the same underlying equilibrium constant from a slightly different angle, chosen depending on which corner of biochemistry or pharmacology happens to be asking the question, the rule most people actually remember from a chemistry class about equilibrium isn't the equilibrium constant at all. It's Le Chatelier principle, named for the French chemist Henri Louis Le Chatelier, who stated it in 1884, though a chemist named Carl Ferdinand Braun independently landed on the same idea 3 years later in 1887, in yet another case of the same discovery, showing up twice from two different directions. The plain version everybody learns goes something like this. Disturb a system sitting at equilibrium by changing the concentration, the temperature, or the pressure, and the system shifts to partly counteract whatever was just done to it. The principle has wandered well outside chemistry as a loose, general metaphor for any settled system responding to a shock. This is part of why it gets invoked constantly in fields with nothing to do with reagents or reaction vessels. Mechanical engineers reach for the identical logic when designing a shear pin, a deliberately weak, sacrificial piece built into a machine specifically to be the first thing that breaks under unexpected stress, relieving the load before it reaches and destroys some far more expensive part of the same system, a direct engineering echo of a chemical system shifting to partly absorb whatever disturbance just hit it. Apply it carefully, the rule works, and it's useful for predicting which direction a reaction leans under new conditions. Add more of a reactant, and the reaction shifts to consume some of the extra amount, producing more product than it would have otherwise. That shifting sits on top of a simpler, separate stoichiometry problem taught earlier in the same course, working out which reactant actually runs out first, called the limiting reagent. Since it's whichever ingredient is used up completely that caps how much product a reaction can physically produce, no matter how much of everything else gets thrown in. Even a reaction with a perfectly favorable equilibrium constant rarely produces the full theoretical amount of product a balanced equation predicts, and chemists track the gap with a separate number called percent yield, the real measured amount of product divided by the theoretical maximum. Since side reactions, incomplete mixing, and product lost during purification all chip away at the real-world result, regardless of what the clean stoichiometric ratio on paper promised. Some pairs of reactants don't even settle on one single fixed stoichiometric ratio at all. Reacting benzene with methyl chloride under the right catalyst can attach one methyl group to the ring, or two, or several more beyond that, all from the exact same two starting ingredients, with the actual balanced equation that ends up describing what happened, decided largely after the fact by how concentrated the reactants happened to be while the reaction was running. One more small crack in the idea that a balanced chemical equation is ever the single final word on what a given set of ingredients will actually do. Gas phase stoichiometry leans on its own quiet simplification too, treating every gas involved as a so-called ideal gas, a mathematical fiction where gas particles take up no volume of their own and never attract or repel each other at all. This is what lets chemists convert cleanly between a gas's volume and the number of moles it represents using one tidy formula. Real gases only behave that ideally when they're spread out thin and kept away from extreme temperature or pressure. And the same convenient assumption that makes gas stoichiometry teachable in an afternoon stops being accurate the moment a gas gets compressed hard enough or cooled down far enough for its own real individual molecules to start crowding each other and getting in their own way. An ordinary car engine runs the same stoichiometric arithmetic under the hood every time it starts, aiming for the exact ratio of air to fuel that burns every last drop of gasoline against every last available oxygen molecule at once, a ratio that works out to roughly 14.7 parts air for every 1 part fuel by weight. For an engine running behind a catalytic converter, real engines rarely sit exactly on that number by choice. Diesel engines deliberately run with extra air beyond what the stoichiometry calls for, since diesel fuel burns less readily and needs the surplus oxygen just to combust cleanly as it's injected, a small, everyday reminder that the ratio a balanced equation demands, and the ratio an engineer actually wants, running through a real machine, aren't automatically the same number. Raise the temperature on a reaction that releases heat, and the equilibrium shifts backward away from products. Since the system treats the extra heat almost like an extra product being pushed into an already crowded room. Squeeze the volume down on a gas phase reaction, and the equilibrium shifts toward whichever side has fewer total gas molecules, since that side takes up less room and partially relieves the added pressure. The naive version of the rule, the one applied by pure gut instinct instead of by actually working through what's changing, fails in at least one specific, well-documented way that trips up plenty of students who think they fully absorbed the principle. Adding an inert gas, one that plays no part in the reaction at all, like helium, into a gas phase equilibrium held at constant volume, does not shift the equilibrium even slightly, even though the total pressure inside the container goes up when the gas is added. The instinct says more stuff in the container should push the reaction somewhere. It doesn't in this specific case because Le Chatelier's principle responds to the partial pressures of the substances actually taking part in the reaction, not to the total pressure of everything in the container combined. And adding an inert gas that doesn't react leaves every one of those individual partial pressures completely unchanged. Only if the container is allowed to expand while the inert gas goes in, diluting everything else along with it, does the equilibrium actually move. The clearest real-world case of the naive version, giving an incomplete answer, not a wrong one exactly, but a dangerously partial one, is the industrial production of ammonia from nitrogen and hydrogen gas. The Haber process, the single chemical reaction most responsible for feeding a large share of the modern world through synthetic fertilizer. The reaction releases heat, about 92 kilojoules for every mole of nitrogen consumed. So, Le Chatelier's principle correctly predicts that running the reaction at a lower temperature should shift the equilibrium further toward ammonia, producing a better yield. That prediction is completely true. It's also incomplete on its own, because lowering the temperature also slows the reaction down according to the separate laws of chemical kinetics, and a reaction that gives an excellent equilibrium yield but takes years to reach it is industrially worthless. Real ammonia plants run at a deliberately chosen compromised temperature, high enough that the reaction actually finishes in a usable amount of time, low enough that the equilibrium yield stays acceptable, a genuine trade-off that Le Chatelier's principle, taken by itself, gives no guidance on whatsoever, since it only describes which way an equilibrium leans, never how fast anything gets there. Nearly all of the nitrogen fertilizer feeding the modern world's food supply still comes out of reactors running that exact compromise today. A piece of everyday agriculture leaning on the gap between what a simple rule predicts and what actually gets built. The principle has its own quiet fine print, too. It's built to describe systems already sitting at or very near genuine thermodynamic equilibrium, and researchers who've studied it carefully have shown that in systems held away from true equilibrium by a constant flow of matter or energy through them, so-called steady states rather than real equilibria, the plain statement of the principle can fail outright. In at least one detailed analysis of the Haber process itself, examined as a flowing, non-equilibrium system instead of a sealed equilibrium one, researchers found the system could show a measured amount of the opposite response from what the simple principle would predict: moderation running backward instead of forward, though not so far backward that it ran away completely. A catalyst changes none of this at all. Meanwhile, it speeds up the forward and backward reactions by exactly the same factor, getting the mixture to whatever equilibrium it was always heading toward faster, without nudging the equilibrium position itself in either direction, even slightly. The principle has wandered a long way from chemistry too, borrowed by fields that have nothing to do with reactions or reagents at all. An economist named Paul Samuelson built his own, formally unrelated version of the same idea in 1947, describing how an economic system responds to some outside change and predicting, by an argument that turns out to be mathematically related to Le Chatelier's own reasoning, that markets typically respond less in the short run than they eventually do, once enough time passes for every constraint to loosen. Biologists reach for a related but explicitly distinct idea, homeostasis, to describe how a living body holds its own internal conditions steady, and the two ideas get compared constantly. But they aren't quite the same mechanism underneath. Le Chatelier's principle describes a passive, almost automatic drift back toward balance, the kind of adjustment that happens on its own once a system is disturbed. Homeostasis in a body is mostly active, run by dedicated biological machinery, spending real energy specifically to hold conditions steady, closer to a thermostat running a furnace than to a spring settling back into its resting shape on its own. Two of the strangest things left in chemistry are still ahead. One is a fight, unresolved by design, over the actual definition of the word acid. The other is a pair of molecules built from the exact same atoms, connected by the exact same bonds that still aren't the same substance at all, not even close, once it actually matters. Here's the acid problem in full, the one this whole tour opened on. The oldest of the three definitions belongs to Arrhenius, and it's also the narrowest. An acid, under this definition, is simply a substance that breaks apart in water to release a hydrogen ion. A base is a substance that breaks apart in water to release a hydroxide ion. It's clean, it's testable with basic equipment, and is the version taught first in almost every classroom on Earth because it maps directly onto the pH scale already covered. It's also badly limited since it only works for substances dissolved in water and plenty of chemistry that clearly behaves like acid-base chemistry doesn't involve water at all. In 1923, two chemists working continents apart without coordinating with each other published the fix for that limitation within the same year. Johannes Nicolaus Bronsted, working in Denmark, and Thomas Martin Lowry, working in England, each proposed essentially the same broader definition independently. An acid, under their rule, is any substance that can hand off a proton to something else. A base is any substance that can accept one. When an acid gives up its proton, what's left behind is called its conjugate base. When a base picks up a proton, what results is called its conjugate acid. The whole reaction gets written as a two-way arrow, acid plus base yielding conjugate base plus conjugate acid, because the reaction almost always runs in both directions at once. Another quiet echo of the equilibrium problem sitting earlier in this same tour. Crucially, this version doesn't require water or even dissociation at all. Dissolve ammonia in liquid ammonia itself, kept as a solvent below its freezing point, and it self-ionizes into an ammonium ion and an amide ion, playing exactly the same structural role that hydronium and hydroxide play in ordinary water. Ammonium salts behave as acids in that solvent. Metal amides behave as bases. None of that involves water even once. Even the proton itself, the thing every Bronsted-Lowry acid is busy handing off, has more than one identity hiding underneath the single word proton. Officially, the generic term for a hydrogen cation is a hydron, and a hydron can turn out to be an ordinary proton or a deuteron, built from a heavier hydrogen isotope, or a triton, built from a heavier one still, and chemistry's naming rules keep separate, precise names for all three specifically because they behave slightly differently in careful measurements, even though every acid-base reaction, taught at an introductory level, treats them all as one interchangeable thing called simply a proton. The Bronsted-Lowry definition produces one of the strangest, most concrete demonstrations that acidity and basicity aren't fixed properties of a molecule at all, only properties of a molecule relative to whatever it's sitting next to. Acetic acid earns its name honestly in water, giving up a proton and turning noticeably acidic in solution. Dissolve that same acetic acid in liquid hydrogen fluoride instead, a solvent that's a far stronger acid than water is. And acetic acid flips roles entirely, behaving as a base, accepting a proton from the hydrogen fluoride rather than donating one of its own. Nothing about the acetic acid molecule itself changed. Only the company it was keeping changed, and that alone was enough to flip which side of the acid-base line it landed on. Chemists studying weak carbon-based acids lean on the same trick deliberately, dissolving them in solvents like dimethyl sulfoxide or acetone nitrile instead of water, specifically because those solvents accept protons more eagerly than water does. This makes otherwise barely acidic molecules act noticeably stronger and easier to measure. Water performs its own small trick along the way. It's what chemists call amphoteric, meaning it can act as either the acid or the base, depending on what it's paired against, and it can even do both roles at the exact same moment in the exact same beaker. Since two water molecules colliding with each other are enough to produce one hydronium ion and one hydroxide ion out of nothing but water reacting with itself. Aluminum hydroxide performs the identical trick with a solid instead of a liquid, reacting as an acid against a strong enough base, and as a base against a strong enough acid, with no fixed identity of its own outside of context. Asking whether water or aluminum hydroxide is really an acid or really a base turns out to be a bit like asking whether a specific person is really a parent or really a child. The question was never well posed in the first place, since the role was always going to depend entirely on who else happened to be standing in the room. Gilbert Lewis published his own far broader definition in that same year, 1923, arriving at effectively the same historical moment as Bronsted and Lowry, but from a completely different direction. Lewis wasn't thinking about protons at all. He was thinking about electron pairs. An acid, in his framework, is anything with an empty spot in its electron structure willing to accept a pair of electrons from somewhere else. A base is anything holding a spare pair of electrons willing to be donated. Lewis argued plainly that limiting the word acid to substances that happen to contain hydrogen made about as much sense as limiting the phrase oxidizing agent to substances that happen to contain oxygen, an arbitrary restriction left over from an earlier, narrower way of thinking about the same underlying chemistry. Lewis's definition is the broadest of the three, and it swallows substances the other two definitions can't even talk about. Boron trifluoride, the same molecule this whole video opened on, is a textbook Lewis acid. Its boron atom sits with an empty orbital, hungry for an electron pair, and the instant it meets ammonia, this is carrying a spare pair on its nitrogen atom. The two snap together into a stable adduct. Chemists write that specific kind of bond with its own dedicated notation, an arrow pointing from the electron pair donor toward the electron pair acceptor, specifically to flag that both electrons in the new bond came from one single side, rather than one from each partner the way an ordinary covalent bond forms. The same small dot chemists use elsewhere to mark a Lewis adduct also shows up written into the formula of an ordinary hydrated salt, like the 7 water molecules clinging to a unit of magnesium sulfate in its common crystalline form, even in cases where those attached water molecules aren't locked into the same kind of formal Lewis adduct bond at all. A notational shortcut borrow across two different situations that don't actually share the same underlying chemistry. Under the Bronsted-Lowry definition, boron trifluoride barely qualifies as anything since it never gives up a proton to anybody, dropped straight into water, instead of dissolving cleanly the way a simple Arrhenius acid would. Boron trifluoride actually reacts with the water and gets consumed, breaking down into boric acid and the related fluorine-containing acid. This makes testing it under the plain Arrhenius rule a bit of a category error to begin with. 3 official definitions, 1 small molecule, 3 different verdicts on what box it belongs in, and every one of those verdicts is correct by the rules of its own definition. The Lewis and Bronsted-Lowry pictures don't just disagree on edge cases either. They can rank the exact same substances in opposite order. Carbon monoxide is, by Bronsted-Lowry standards, a very weak base, barely interested in picking up a stray proton at all. By Lewis standards, that same carbon monoxide molecule forms a strong, stable adduct with boron trifluoride, ranking as a perfectly respectable electron pair donor. Ask which theory is right about carbon monoxide's basicity, and both are correct at once. Just about two different things that happen to share the English word basic. However, chemists choose to define an acid, measuring exactly how strong one is, loops straight back to the equilibrium chemistry from earlier in this tour. An acid dissolving partway in water is just another reversible reaction sitting at its own equilibrium point. And the acid dissociation constant that describes how far that particular equilibrium leans toward splitting apart is the exact same kind of number as the equilibrium constant covered earlier, run through the identical negative logarithm trick that turns hydrogen ion concentration into pH in the first place. Benzoic acid's own dissociation constant, the same one behind the quadratic equation and the measured pH of 3.11 from earlier in this tour, is really just a Bronsted-Lowry acid strength measurement, an equilibrium constant, and a direct input into the Gibbs free energy equation, all sitting inside one single unremarkable number. Most students meet for the first time as a bare figure printed in a reference table, with no sense of how many separate pieces of this entire tour are meeting each other inside it. Even inside the Lewis framework alone, chemists don't have one single universal ranking of acid strength that works for every comparison. This is its own small extra layer of the same underlying problem. Lewis acids and bases get sorted informally into hard and soft categories, a classification system built in 1963, where hard means small and hard to polarize. Roughly things like the bare proton or an alkali metal ion, and soft means large and easily polarized, roughly things like a silver ion or a platinum atom in a low oxidation state. Hard acids pair up more strongly with hard bases, and soft acids pair up more strongly with soft bases, mismatched pairs bonding more weakly than matched ones. A rule that turns out to be useful for predicting which combinations of Lewis acids and bases will actually react favorably. Digging into the thermodynamics behind that rule shows hard pairings gain their extra stability mostly from enthalpy, the raw energy released by bond formation, while soft pairings gain theirs mostly from entropy instead. The same idea from earlier in this tour, showing up again in a completely different corner of the subject. Chemists have gone further and built an actual quantitative equation for predicting the strength of a Lewis acid-base interaction, assigning every acid and every base its own pair of numbers, representing how much of its bonding tendency is electrostatic and how much is covalent, and multiplying the matching numbers together to predict the bond strength directly. Plot enough of those numbers against each other and something uncomfortable falls out. There is no single fixed ranking of which Lewis acid is strongest, full stop. The ranking depends entirely on which base it gets tested against, and the order can flip depending on the pairing. This means even asking a clean question like which is the stronger Lewis acid doesn't always have one fixed answer waiting. Sterics complicate the picture on top of all of that. A bulky, heavily substituted version of pyridine, loaded up with two large tert-butyl groups right next to its nitrogen atom, still reacts cleanly with plain hydrogen chloride to form a salt, exactly the way ordinary pyridine would, because a bare proton is tiny enough to squeeze in next to the nitrogen regardless of how crowded the surrounding molecule gets. That same bulky pyridine refuses to react with boron trifluoride at all, even though boron trifluoride is a perfectly good Lewis acid by every electronic measure available, purely because boron trifluoride is physically too bulky itself to fit into the crowded space the tert-butyl groups leave behind. Two acids, one proton-sized and one molecule-sized, get two completely different answers from the exact same base for reasons that have nothing to do with electron pairs or protons at all and everything to do with simple physical crowding. None of this even covers the geochemists who ran into acid-base reactions the Bronsted-Lowry definition can describe at all, and built a fourth theory just to patch the hole. Melt magnesium oxide and silicon dioxide together at high temperature, and they react to form a new mineral, with no proton moving from one molecule to another anywhere in the reaction, since neither reactant has a proton to give in the first place. The Bronsted-Lowry framework, built entirely around proton transfer, simply has nothing to say about that reaction. Geochemists reach instead for a separate rule called the Lux flood theory, defined around oxide ions rather than protons, where an acid is a substance that accepts an oxide ion and a base is a substance that donates one. Under that fourth definition, magnesium oxide counts as a base, and silicon dioxide counts as an acid. And the natural mineral olivine gets described quite literally as a compound built from one basic oxide and one acidic oxide fused together, a description that would mean nothing at all under any of the first three definitions this whole segment has already covered. So the count really depends on how generously the counting gets done. Arrhenius, the oldest and narrowest. Bronsted-Lowry, built around the proton, generalizing Arrhenius and working outside water. Lewis, built around the electron pair, broader than both and swallowing substances neither of the other two can classify at all. A fourth, the Lux flood theory, built for reactions involving oxide ions that none of the first three can describe. Four separate, published, actively used definitions for one of the very first words taught in a chemistry classroom, and every single one of them is the correct answer to a slightly different question. Lewis's own original wording for his definition, written in 1923, described an acid as any substance able to use a spare pair of electrons from another molecule to complete the stable arrangement of one of its own atoms, deliberately framed to include far more chemistry than the proton-centered picture Bronsted and Lowry were publishing that same year. The hard and soft classification built on top of Lewis's definition comes with its own working lists. Chemists actually use day to day. Typical hard acids include the bare proton itself, ordinary alkali and alkaline earth metal ions, and boron-based compounds. Typical soft acids include silver ions, certain low oxidation state platinum and nickel compounds, and other large, easily squished metal centers. Typical hard bases include ammonia, plain water, and the fluoride and chloride ions. Typical soft bases include organic phosphorus compounds, sulfur-based ethers, carbon monoxide, and the iodide ion. An amine base, sitting on the harder end of that spectrum, will actually displace a softer phosphine base, clean off a boron trifluoride adduct, if the two are made to compete for the same acid, a real, testable, hard versus soft tug of war playing out in a single reaction flask. The quantitative version of hard-soft strength prediction, assigning every acid and base its own measured pair of numbers, traces back specifically to work by the chemists Drago and Wayland, whose names are still attached to the underlying equation used to predict exactly how strongly two given partners will bond before anyone even runs the reaction. Lewis bases end up doing quiet, practical work in the pharmaceutical industry too. Attaching a chiral Lewis base onto a metal catalyst can force that catalyst to build only one of two possible mirror image products instead of an equal mixture of both, a technique called asymmetric catalysis. And the industrial production of the blood pressure medication mibifradil leans on exactly that trick, using one specific chiral Lewis base to steer the entire manufacturing process toward the single correct mirror image form the drug actually needs. The same handedness problem waiting at the very end of this tour, already deciding how a real medicine gets made at industrial scale. The next stop goes back to the very beginning of the atom, to the rule chemistry students memorize before almost anything else. The order electrons fill up as an atom gets built, one proton and one electron at a time, moving across the periodic table. Getting to that rule took physics most of the 20th century's first 3 decades, and it took several tries. Niels Bohr's original 1913 model of the atom used a single number to describe an electron state, enough to explain a narrow slice of hydrogen's spectrum, but nothing more complicated. Arnold Sommerfeld added a second number in 1915 and a third in 1919, trying to account for how atomic spectra shifted inside electric and magnetic fields. None of it quite worked. Something was still missing. The spectra kept refusing to line up. In 1923, Bohr wrote directly to a younger physicist named Wolfgang Pauli, more or less asking for help saving the whole shaky framework of what's now called the old quantum theory. Pauli's answer, worked out over the next 2 years, was to add a fourth number entirely, one that could only take two possible values, and to propose a rule now called the exclusion principle, that no two electrons inside the same atom are ever allowed to share all four of those numbers together. That single rule is the real reason atoms build up the way they do, layer by layer, instead of every electron just piling into the lowest possible slot. Electrons belong to a class of particle physicists called fermions. No two fermions in the same system are ever allowed to share an identical state, full stop, which is the deeper reason every ordinary orbital tops out at exactly 2 electrons and not one more. 2 years later, Erwin Schrödinger's wave equation showed up and produced 3 of Pauli's 4 numbers as a direct mathematical consequence of solving the equation for a hydrogen atom, finally putting solid mathematics underneath what had been mostly educated guesswork until then. Pauli's 4th number, electron spin, has a direct cousin sitting inside the atomic nucleus itself, and that cousin turns out to be the entire reason 2 enormous pieces of modern medical equipment exist at all. Protons and neutrons packed together inside a nucleus in pairs whenever possible, each pair canceling its own, spin out to 0. This leaves nuclei with an odd number of protons or neutrons carrying a small, leftover nuclear spin of their own in the same units used for ordinary electron spin. That leftover nuclear spin interacts with an external magnetic field in a way that's directly detectable, and the entire technique of nuclear magnetic resonance spectroscopy, the tool organic chemists lean on constantly to work out an unknown molecule's structure, runs on exactly that interaction. Widen the same underlying physics from a small test tube to an entire human body, and it becomes magnetic resonance imaging, an MRI scan, reading the nuclear spin of ordinary hydrogen nuclei scattered throughout soft tissue to build a detailed picture of the inside of a living body with no surgery and no radiation involved. A piece of hospital equipment most people have sat inside at some point without ever being told it's running on the same fourth quantum number. This whole stop opened with the word quantum number stretches well past chemistry once physicists start describing particles smaller than the atom altogether. And the four numbers this whole stop is built around are really just the chemistry sized version of a much larger idea. Subatomic particles carry their own separate quantum numbers with no equivalent anywhere in ordinary atomic chemistry at all. Properties physicists lump together under the general heading of flavor, tracking things like electric charge and separate bookkeeping numbers for whole categories of particle called leptons and baryons. Most of those quantum numbers simply add up on both sides of a particle reaction, the way ordinary arithmetic would suggest. A smaller handful, called parity among them, work by multiplying instead, conserved as a product rather than a sum, a distinction so far removed from anything a chemistry student ever needs that it's worth mentioning, mainly to show how far the idea a chemistry classroom introduces first actually reaches once physicists pick it up and keep running with it. Physicists studying the atomic nucleus itself needed their own dedicated quantum number too, and it arrived surprisingly late. Werner Heisenberg proposed an early model of how protons and neutrons bind together in 1932, and it took until 1937 for Eugene Wigner to introduce a new quantum number called isospin, the first one in physics built to track an internal property with no equivalent symmetry anywhere in ordinary, everyday space, treating the proton and the neutron as two faces of one single underlying particle, distinguished only by which isospin value each one happens to carry. Even the shell-filling order itself got discovered more than once, in the same pattern that keeps showing up across this entire subject. A little-known physicist named Charles Janet worked out the correct filling order in 1929. Erwin Madelung rediscovered the identical rule independently in 1936, and Madelung's name is the one that stuck. So most textbooks now call it Madelung's rule, even though Janet published it 7 years earlier. A separate scientist, Kleczkowski, later worked out a theoretical justification for why the rule works at all. This is why some countries teach it under a third name entirely, Kleczkowski's rule, for the exact same pattern. 3 names, 1 rule, discovered independently at least twice and formally explained by a third person after the fact. The exact same pattern this tour has already run into with VSCPR and with Le Chatelier's own principle, different scientists in different countries arriving at the identical answer without knowing anyone else was even asking the same question. The rule itself is simple to state and gets simplified even further in most classrooms. Fill the lowest energy orbitals first, and the order runs 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and onward, climbing the periodic table roughly diagonally, instead of shell by clean shell. This already surprises plenty of students the first time they see it, since the 4s orbital fills before the 3d orbital does. Out of the order the plain shell numbers would suggest, helium itself sits in a permanently awkward spot on the periodic table because of exactly this filling order. By its raw electron configuration, helium belongs with hydrogen at the very top of the leftmost column, since both fill only the innermost s orbital and nothing else. Every periodic table actually printed sticks helium at the far right instead, alongside neon, argon, and the other noble gases, because helium behaves chemically like a noble gas, almost completely inert, rather than behaving anything like the reactive alkali metals hydrogen technically sits above. The placement is a chemistry first decision overriding a raw electron configuration first one, and it's still debated among specialists today whether the convenience of grouping helium with gases it actually resembles should outweigh the structural logic that says it belongs somewhere else entirely. Two elements break their own rule almost immediately after it's introduced, and they break it in a way that gets explained with a tidy little story that turns out not to hold up under scrutiny. Chromium is predicted to fill as 3d4 4s2. Measured directly, real chromium is 3d 5 4s1, with one electron jumping clean out of the 4s orbital and over into the 3d orbital, leaving the 3d shell exactly half full, and the 4s shell with only one electron in it instead of two. Copper does the same jump one column over, predicted as 3d9 4s2. Real copper measures out as 3d10 4s1, filling the 3d shell completely instead of leaving it one electron short. The usual classroom explanation for both jumps is that half-filled and fully filled subshells carry some special, extra stability that makes the jump worthwhile. That explanation gets directly undercut by its own next-door neighbors on the periodic table. Tungsten, sitting in the exact same column as chromium one row further down, does not make the same jump at all, staying at its plainly predicted configuration instead. Niobium, one column over from tungsten, does jump, but lands on a configuration that isn't half filled or fully filled either way, breaking the pattern in a direction the tidy explanation can't even account for. The rule taught to explain the two most famous exceptions doesn't reliably predict which other elements will need the exact same kind of exception. This means it was never really an explanation at all, just a label pasted onto an observation after the fact. The deeper problem sitting underneath all of it is a hidden assumption nobody states out loud while teaching the filling order in the first place, that a given orbital carries one fixed energy value, no matter what atom it belongs to or how many other electrons are crowded around it. It doesn't. The energy of the 3D orbital shifts depending on how many electrons already sit in the atom and how much positive charge is packed into the nucleus, pulling on all of them at once. This is exactly why pulling electrons back off an atom doesn't reverse the order they went in. Ionize iron, stripping electrons away one at a time, and the very first electrons to leave come out of the 4s orbital, not the 3D orbital, even though 4s filled up first going in. That reversed order holds for every single element across that whole row of the periodic table, without exception, and it makes total sense once the fixed energy assumption gets dropped, because a positively charged iron ion has a completely different balance of forces inside it than a neutral iron atom does. And there's no real reason to expect the two to behave identically just because one turned into the other by losing a couple of electrons. Even the supposedly settled question of which orbital actually sits lower, 4s or 3d, in a neutral, unionized atom, is still being argued over in the research literature. Researchers, including Eric Seri, have published analyses arguing that the 3d orbital, not the 4s orbital, is the one occupied preferentially in these atoms, directly contradicting the framing printed in most textbooks, including the title most of those same textbooks give the whole topic, a question first-year students are handed as a settled, memorizable fact, is, at the research level, an open argument among specialists who study exactly this for a living. The exceptions pile up further out on the table, and the tidy stability story runs out of road entirely. Thorium, stripped down to a bare, triply charged ion, measures out with one electron sitting in an f orbital. Put that same thorium atom into most of its real chemical compounds, and its outermost electron sits in a d orbital instead. A completely different configuration depending purely on chemical context instead of on the atom's identity. Copper metal itself, measured carefully, isn't cleanly one configuration or the other at all. Real measurement describes it as roughly 90% one arrangement and 10% the other, blended together rather than settled on a single, clean answer. This is a strange thing to learn about an element every student is handed a single, definite electron configuration for on page 1. Even chromium hexacarbonyl, a compound built from one chromium atom surrounded by 6 carbon monoxide molecules, gets its central chromium atom's configuration described one way under the simplified crystal field picture chemists use for a quick prediction, and a subtly different way once the fuller molecular orbital treatment. The same theory from earlier in this tour gets applied properly. Predictions for the heaviest artificial elements, the ones sitting past the edge of what's actually been made and tested in a lab, keep needing extra caveats too. Element 121 is predicted to skip straight past the pattern that's held for every lighter element before it, filling a p orbital ahead of schedule instead of the g orbital. The plane rule would call for next, purely because of how close together several different orbitals' energies become out at that end of the table. And relativistic effects, electrons moving fast enough for special relativity to matter, start reshuffling the whole filling order even further once atoms get heavy enough. None of that heaviest element chemistry has actually been tested against a real atom yet either, since elements past a certain point exist for only fractions of a second before decaying. This means every one of these predictions is a calculation standing in for an experiment nobody has managed to run. Even one single correctly written electron configuration doesn't fully pin down an atom's actual energy. This is a strange thing to learn after spending an entire unit memorizing exactly how to write one. The same configuration can correspond to several different specific energy levels depending on how the individual electrons, spins, and orbital motions happen to line up relative to each other, and chemists tack on an extra label called a term symbol, specifically to distinguish those different possible arrangements apart. Working out an atom's real emission spectrum, the specific colors of light it gives off, actually requires that extra layer of labeling on top of the plane configuration. And it was that painstaking spectral analysis, matching real observed light against predicted term symbols, that let physicists confirm which ground state electron configurations were actually correct in the first place, back before any of this could simply be calculated from first principles the way it can today. A close cousin of this same problem shows up one level up the periodic table in the trends students are taught to expect as a matter of course. Electron affinity, how much energy gets released when a neutral atom grabs one extra electron, is supposed to climb steadily, moving left to right across a row, and supposed to be highest for the smallest, most electronegative atoms. By that logic, fluorine, sitting at the very top of its column and famously the most electronegative element on the entire table, should have the highest electron affinity of any halogen. It doesn't, chlorine does. That surprises almost everyone the first time. Fluorine is small enough that the extra incoming electron has to squeeze in among electrons already packed unusually close together around such a small nucleus. And the resulting repulsion cuts into the energy released by more than the plain trend predicts, handing the actual record to chlorine, one row down, instead of to fluorine at the top where the simple rule says it belongs. A similar wrinkle shows up in electronegativity itself, moving down group 13, boron's own family. The plain trend says electronegativity should fall steadily moving down any column as atoms get bigger and hold their outer electrons more loosely. Moving from boron down to aluminum, it does fall right on schedule. Moving on past aluminum, it reverses and starts climbing again for the rest of the column. Because poor shielding from a layer of inner D and F electrons lets the nucleus's pull sneak back up on the outer electrons in a way the plain top to bottom trend never accounts for. Metallic character itself runs on the mirror image of that same electronegativity trend. Climbing as an element sits further down a column and further left across a row. Since a metal's whole identity comes down to how loosely it holds its own outer electrons, and every one of the exceptions already covered in this stop, the electron affinity reversal, the group 13 electronegativity, dip and rebound, ripples forward into exactly where the line between metal and non-metal actually falls to, since that line is drawn from the very same trends that keep breaking their own rules. A third trend: how eagerly a substance donates or accepts electrons during an actual reaction instead of just holding on to them, called nucleophilicity and electrophilicity, tracks electronegativity loosely across the periodic table, but comes with its own explicit warning attached even in the reference material describing it. Since the specific molecular surroundings a substance finds itself in during a real reaction can swing its behavior enough that the periodic trend alone can't reliably predict it, full stop, no matter how carefully the underlying electronegativity numbers get read. Three different textbook trends taught as reliable rules of thumb across the whole periodic table, each carrying at least one well-documented, well-explained exception that the simple version of the rule leaves the student with no way of predicting in advance. Even the plain business of writing an electron configuration down on paper carries a small, quiet ambiguity most students never notice. Chemists almost always abbreviate a long configuration by borrowing the nearest smaller noble gas as a stand-in for its filled inner shells. So phosphorus, instead of being written out as 1s2 2s2 2p6 3s2 3p3, just gets written as the symbol for neon in brackets followed by 3s2 3p3, since neon already accounts for everything phosphorus shares with it. Even the order the remaining symbols get written in isn't fixed by any hard rule. Titanium's configuration gets written by some chemists as argon in brackets 4s2 3d2, following the order the electrons actually filled in, and by other chemists as argon in brackets 3d2 4s2, following the order those same electrons would come back off again if the atom were ionized. And both versions correctly describe the identical atom, depending purely on which convention the writer happens to prefer. The whole idea of a fixed electron configuration starts to dissolve entirely once atoms stop sitting alone. Every atom's underlying drive to reach a full outer shell, the same noble gas-chasing instinct that explains why sodium and chlorine form a stable salt in the first place, is really just electron configuration talk, dressed up as a stability story. That story works cleanly for small, simple molecules, and starts blurring at the edges almost immediately elsewhere. Push enough atoms together into a solid block of material, and the whole concept of one atom's private individual electron configuration stops being useful at all, since the one separate energy levels smear together into wide continuous bands shared across the entire piece of material, a completely different framework called band theory that chemistry students studying metals and semiconductors have to learn essentially from scratch. Because the atom by atom filling picture that worked everywhere else in this tour simply has nothing left to say once matter gets bundled together in bulk. The last stop on this tour carries the biggest stakes of anything covered so far, and it starts with something as ordinary as a pair of hands. Two hands held up next to each other with the palms facing the same direction are identical in every measurement that matters. Same number of fingers, same bone lengths, same angles between joints. Lay one directly on top of the other, and they never quite line up because a left hand is the mirror image of a right hand, not a rotated copy of it. And no amount of turning or flipping in 3 dimensions ever makes one into the other. Chemists call that property chirality, borrowed straight from the ancient Greek word for hand, and it turns out an enormous number of molecules share the exact same geometric trap human hands are stuck in. A chiral molecule is one that cannot be superimposed on its own mirror image, and the two mirror image versions are called enantiomers. Formally, this usually comes down to one particular atom inside the molecule, called a stereocenter, holding 4 different groups attached to it in a tetrahedral arrangement. Swap any 2 of those 4 groups, and the molecule that results is a genuine mirror image of the original, not just a rearranged version of the same thing. Carbon is the most common stereocenter by far, since carbon naturally forms 4 bonds arranged tetrahedrally, but it's not the only option. Nitrogen, phosphorus, silicon, and sulfur can all serve as stereocenters too, under the right conditions. And even a whole metal atom sitting at the center of a coordination complex can carry the same kind of handedness. Chirality doesn't even require a single distinguishable center at all in every case. Some molecules twist around a whole axis rather than a single point, called axial chirality, and others get their handedness from a warped, non-planar shape instead of any specific atom, called inherent chirality, the same geometric trick that gives certain screw-shaped organic molecules, appropriately named helicenes, their own left and right-handed versions. The 2 mirror image versions of a chiral molecule share every ordinary physical property chemists usually measure: the same melting point, the same boiling point, the same solubility, the same color, all identical between the 2. Where they differ is in how they interact with anything else that's itself chiral. And the natural world is absolutely stuffed with chiral molecules already sorted onto one side or the other. Nearly every biologically important molecule on the planet exists in only one of its 2 possible mirror image forms. Every naturally occurring sugar used by living cells, essentially every amino acid that builds every protein in every organism. And both strands of the DNA and RNA that carry genetic information all commit to one-handedness and stick with it consistently across the entire tree of life. Why life ended up locked onto one side and not the other, honestly, is not settled science, and it's worth saying plainly rather than pretending there's a tidy textbook answer. Most researchers currently lean toward the idea that it was close to a coin flip, an accident of early chemistry that happened to land one way and then got locked in permanently once biology started building on top of it. Since once a system commits to one-handedness, mixing in molecules of the opposite handedness tends to gum up the machinery instead of help it. There is a real, alternative, actively studied idea sitting alongside that one, not yet settled either way. About 17% of the light radiating off young, forming stars is circularly polarized, meaning it twists in a specific handed direction as it travels. And some researchers have proposed that this polarized starlight could have selectively destroyed one mirror image version of early amino acids forming out in comet dust before life on Earth had even gotten started, tipping the scales toward one-handedness before biology ever had the chance to choose for itself. Neither explanation has won out over the other. Both remain live possibilities in a question nobody has closed. Chirality causes real, measurable, sometimes dangerous differences the instant it meets another chiral system, and human biology is built entirely out of chiral parts. This means every one of us is constantly, unavoidably testing chirality on ourselves without noticing. The molecule carvone smells distinctly like spearmint in one of its two mirror image forms, and distinctly like caraway seed in the other. Identical atoms, identical bonds, different smell entirely. Because the receptors lining the human nose are themselves chiral structures, and a chiral receptor responds differently to two molecules that are otherwise perfect mirror twins of each other, the same way a right-handed glove only really fits a right hand. Taste runs the same trick. Left-handed amino acids, the kind that actually build proteins in every living thing, generally taste close to bland, while their right-handed mirror twins, essentially absent from natural biology, tend to taste sweet instead. Pharmaceuticals turn the same effect from a curiosity into something with real stakes. The antidepressant citalopram commonly gets sold as a racemic mixture, meaning a 50-50 blend of both mirror image forms mixed together in the same pill. Careful study eventually showed that only one of the two mirror forms, now sold separately under the name escitalopram, actually accounts for the drug's therapeutic benefit, meaning half of every dose of the older mixed pill was essentially doing nothing useful at all, riding along as dead weight next to the half that actually worked. Penicillamine pushes the same idea into dangerous territory rather than just wasted dosage. One mirror image form, D-penicillamine, is a real, useful medication prescribed for rheumatoid arthritis and used in chelation therapy to pull heavy metals out of the body. Its exact mirror twin, L-penicillamine, is toxic, actively interfering with the body's ability to use vitamin B6. Same formula, same atoms, same bonds, and one version treats a disease while the other actively harms the person taking it. That's not a rounding error. It's not an academic curiosity either. That's the entire difference between medicine and poison, sitting inside a purely geometric property that has nothing to do with the atoms or bonds themselves, and everything to do with which way the whole structure happens to be flipped in space. A distinction no ordinary chemical test built around mass, melting point, or elemental composition could ever catch, since every single one of those tests comes back reading exactly identical for both. The discovery of chirality itself took decades to piece together, and the pieces came from separate directions before anyone connected them. A French scientist named Jean-Baptiste Biot noticed as early as 1812 that certain substances would twist a beam of polarized light as it passed through them, rotating it either clockwise or counterclockwise, depending on the substance, a phenomenon that became important later on in the sugar industry and in pharmaceutical testing, since measuring that twist turned out to be a fast, reliable way to identify and measure chiral compounds without any more elaborate equipment. It took until 1848 for Louis Pasteur to work out that the effect had an actual molecular cause instead of being some accident of measurement, and he proved it in a striking, almost absurdly hands-on way. Pasteur took a batch of sodium ammonium tartrate, a salt that forms as a 50-50 racemic mixture, grew it into tiny crystals, and then sat down with a microscope and a pair of tweezers and physically separated the left-handed crystals from the right-handed ones by hand, one crystal at a time, based purely on their subtly different shapes. It's one of the strangest, most patient experiments in the history of chemistry. And it's also the experiment that proved molecular handedness was real, done years before anyone had any working theory at all for why a molecule would have handedness to begin with. Pure, careful observation, running well out ahead of any actual explanation. The word chirality itself didn't get coined until decades later by Lord Kelvin in 1894, borrowing the Greek word for hand directly. For a long stretch after that, chemists assumed chirality was a trick unique to organic carbon-based chemistry, a misconception that held until 1911, when a chemist named Alfred Werner managed to separate the two mirror image forms of a purely inorganic cobalt compound nicknamed Hexol, proving that molecular handedness had nothing to do with carbon specifically at all, and that a metal atom sitting inside a purely mineral compound could be every bit as chiral as any organic molecule built by a living cell. Chirality even shows up in minerals with no biological origin whatsoever. Quartz crystallizes into left-handed and right-handed forms straight out of molten, non-chiral liquid silica, purely as an accident of how the crystal happens to lock into place as it cools. No life involved anywhere in the process. Chirality can even reach out and reorganize a whole liquid, not just a single molecule inside it. Certain liquid crystal materials, the same broad family of substances used inside ordinary flat screen displays, naturally settle into what's called a nematic phase, where the individual rod-shaped molecules all point in roughly the same direction without otherwise being locked into any fixed position. Stir in just a small amount of a chiral additive, even a tiny fraction of the total liquid, and the entire nematic phase reorganizes itself into a different arrangement entirely, called a cholesteric or chiral nematic phase, where the average direction the molecules point gradually twists into a slow spiral running through the whole sample, a large-scale, visible structure imposed on billions of molecules by the geometric handedness of a comparatively tiny number of chiral guest molecules mixed in among them. It wasn't until the early 1970s that researchers actually directly confirmed that the human sense of smell is capable of telling chiral molecules apart at all. More than a century and a half after Biot first noticed light bending through a jar of the stuff, even sorting out which molecules count as chiral in the first place turns out to carry its own fine print, familiar by now from everything else this tour has covered. Butane, an extremely simple molecule, does pass through chiral shapes as it rotates around its own central bond, but chemists still call butane achiral overall, because the barrier to that rotation is so low, only a few kilocalories per mole, that the molecule flips between its mirror image shapes far too fast at room temperature for the two forms to ever be separated or treated as distinct substances in practice. A related ring-shaped molecule, a version of dichlorocyclohexane, does the same thing through a different kind of internal flip called a chair flip, interconverting its own mirror images constantly enough that it also gets labeled achiral in practice, despite passing through chiral shapes along the way. Chemists even draw a formal, if somewhat arbitrary, timing line for this, treating 1,000 seconds as the rough cutoff for whether two mirror image forms count as separable in any practical laboratory sense or not. Molecules locked into one shape only because rotation around a single bond is unusually restricted get their own separate name, atropisomers, distinct from ordinary chirality, even though the geometric trapping them is functionally the same one. Chirality can even come from nothing more exotic than swapping one isotope of hydrogen for another. A benzyl alcohol molecule with one ordinary hydrogen atom replaced by its heavier isotope, deuterium, becomes measurably chiral and measurably rotates polarized light purely from that one atomic substitution, even though the exact same molecule built entirely from ordinary hydrogen isn't chiral at all. The handedness, in that case, comes from nothing more than one atom weighing slightly more than its otherwise identical twin. The frontier of this whole problem has moved somewhere strange in recent years into machine learning, predicting how a chiral molecule will actually behave. This mirror form eludes first through a specialized chromatography column, or exactly how strongly a given molecule rotates polarized light, has turned out to be difficult enough that chemists have started training computer models on huge datasets of known chiral compounds just to make educated predictions, rather than working every case out from first principles by hand, using tools like molecular fingerprints, fixed length strings of numbers that capture a molecule's local structure, and newer neural network encodings trained directly on huge libraries of known molecular structures, borrowed wholesale from outside chemistry. Even that approach runs into its own version of the same underlying problem this entire tour keeps circling back to. The standard shorthand chemists use to type a molecule's structure into a computer, called Smiles notation, marks chirality with a pair of small symbols, an at sign or a doubled at sign, sitting right next to the stereo center. Neural networks trained to read that notation and predict chirality related properties routinely go through an early phase of training where they visibly confuse the two symbols, mixing up left-handed and right-handed versions of the exact same molecule before eventually learning to tell them apart reliably. Even the machines meant to finally settle every open question in this subject have to learn the slow way that two things built from identical atoms and identical bonds can still be different in ways that matter depending purely on which way they're turned. Not every chiral molecule needs a single obvious stereocenter to carry its handedness either. This trips up plenty of students who go looking for chirality purely by hunting down a tetrahedral carbon with four different groups on it. A molecule called binol, built from two connected naphthalene rings, gets its chirality from an entire axis running through the molecule instead of any one atom, twisted, so the two halves can't rotate freely past each other, a property called axial chirality. A related molecule, one particular geometric form of cyclooctene, gets its chirality from an entire plane instead, called planar chirality, arising purely from the ring being too small and too rigid to let a certain double bond flip to its opposite ordinary geometric arrangement. Ferrocene, an unusual sandwich-shaped molecule with an iron atom trapped between two flat carbon rings, can pick up its own chirality the same planar way once enough different substituents get attached around its rings. None of these examples involve a single carbon atom holding four different groups at all, which is the only picture most introductory chemistry courses ever actually show. Chemists also grade real samples of a chiral substance by how cleanly they've been separated, rather than treating chirality as a strict either-or property in practice. A sample containing only one of the two mirror image forms, with none of the other present at all, gets called an enantiopure. A sample containing an uneven mix of both gets described by its enantiomeric excess, a single number that captures how lopsided the mixture actually is. So, a sample described as 40% enantiomeric excess of one form actually contains 70% of that form and 30% of its mirror twin, the 40 being the gap between the two, instead of either raw percentage on its own, separating a real racemic mixture back into its two pure mirror image components. Once it exists as an even 50-50 blend, usually means reacting the whole batch with a second chiral substance pulled from what chemists call the chiral pool, naturally occurring, already sorted chiral molecules like malic acid, extracted from unripe apples, among other sources, that react differently with each of the two mirror image forms, and let a chemist pull the resulting compounds apart by ordinary crystallization or chromatography once they're no longer perfect mirror twins of each other. Metal complexes get their own separate labeling system for handedness entirely, borrowed from Greek letters rather than the plain left and right words used for organic molecules. A well-studied ruthenium complex built with three identical ring-shaped ligands twisted around the central metal atom like a three-bladed propeller, gets one of its two mirror image forms labeled with the Greek letter lambda for a left-handed twist, and the other labeled delta for a right-handed one, a completely separate naming convention from the plus and minus signs chemists use elsewhere to describe which direction a substance actually rotates polarized light in a real measurement. And the two labeling systems don't always line up in any obvious, predictable way. Some chiral substances rotate light by such a tiny, vanishingly small amount that no realistic laboratory measurement can actually detect it at all, a condition with its own dedicated name, cryptochirality, real molecular handedness, sitting there in the structure, but functionally invisible to the one classic instrument, the polarimeter, built specifically to catch it. Chemists even keep a whole extra vocabulary just for grading how well a real sample has been sorted. Any sample that isn't a perfect 50-50 racemic blend gets labeled scalemic, and inside that category, a sample counts as an enantiopure only if every molecule in it shares the identical handedness, or enantio enriched if it's tipped unevenly toward one side without having fully purged the other, which means the plain word chiral on its own was never actually enough to describe a real bottle sitting on a real laboratory shelf. None of this adds up to chemistry being broken or badly taught or secretly incoherent underneath a friendly face. It adds up to something closer to the opposite. A subject gets to be this useful, this reliable, this widely applicable to everything from a fertilizer plant to a heart medication, because it's willing to hand a beginner a simplified working picture first and worry about the mess underneath later, once that beginner actually has somewhere to stand. The atom's shape gets taught as tidy hybrid orbitals before it gets taught as a smeared out, delocalized cloud, because the tidy version is teachable and the smeared out version, correct as it is, isn't, not on day one. Entropy gets taught as disorder, a word researchers studying chemistry education have directly flagged as a real source of confusion, because Disorder gives a beginner something to hold on to before they're ready for a rigorous count of microscopic arrangements. Oxidation numbers get handed out as though they were real physical charges because the pretend version balances equations just as well as the true Messier electron distribution would, with a fraction of the difficulty. And underneath all of that sits the strangest fact of all, the one this whole tour opened on. One of chemistry's most basic words still carries three, arguably four, separate official readings that nobody has ever forced into full agreement. And it turns out the field has never actually needed to force them. Arrhenius handles the simple cases dissolved in water. Bronsted and Lowry handle the ones that step outside water entirely. Lewis handles the ones that step outside protons altogether. Geochemists reach for a fourth rule when even that isn't enough. Each one answers a real, useful question, and the field just keeps all of them running side by side on purpose, because insisting on one single, fixed reading of the word acid was never actually necessary to get the work done. The models taught first are simplified on purpose, not out of laziness. The two ideas that trip up more students than anything else in the subject, entropy and equilibrium, are hard for documented, studied reasons, not because anyone using them is careless. And the field keeps a completely straight face while quietly running more than one official reading of its own most basic terms at the same time, and that turns out to be a perfectly workable way to run a science. Teaching the fully rigorous version of any of this on day one was never really an option anyway. Nobody starts an introductory class with molecular orbital theory, the statistical version of entropy, and activity coefficients, because a beginner has nowhere yet to hang any of it, no prior intuition for those ideas to attach themselves to. Every subject starts people off with the balloon shapes, the disorder metaphor, the plain concentration numbers, because those simplified pictures are learnable, fast, and sound enough to be useful. And it moves people on to the messier truth only once the simplified version has already done its job of building somewhere for the messier truth to land. That's not a flaw hiding underneath the subject. It's closer to the shape of the whole thing, visible only once someone actually gets close enough to see it.